Hello there, and welcome to Physics with William, a quiet place where curiosity slows down a little and the world makes sense one idea at a time. Wherever you happen to be right now, whether the room around you is bright with daylight or softened by evening shadows, it's good to have you here. Tonight, or this moment, or whatever time it is for you, we're going to talk about something that surrounds you constantly, something that moves through your home, your body and the planet itself without making a sound or leaving a visible trace. It's something you rely on every day without ever needing to think about it, and yet it quietly shapes nearly every modern experience you have. We're going to talk about electromagnetic fields. That phrase can sound technical at first, even intimidating, but the reality of it is much gentler and much closer to daily life than it seems. Electromagnetic fields are not exotic objects locked away in laboratories or hidden inside equations. They're already here, stretching invisibly between power lines, flowing from your phone, guiding compasses, carrying radio voices and holding atoms together. You don't need special instruments to depend on them, you already do. Every time a light turns on, every time a message travels wirelessly, every time your heart beats in rhythm with signals from your brain, electromagnetic fields are quietly doing their work. What makes them especially fascinating is that for most of human history, no one knew they existed. People felt their effects long before they understood their cause. A compass needle turning north felt almost magical. Static sparks jumping from fabric on a dry day felt mysterious. Lightning tearing through the sky inspired fear, reverence and stories long before anyone suspected. It followed the same rules as a battery or a magnet. These invisible forces were always there, shaping the world in subtle ways, long before we learned how to name them. Before we go any further, it's worth pausing for just a moment and asking something simple. Where are you listening from right now? Are you at home, lying down, maybe letting your thoughts slow, or are you somewhere else entirely, moving through your day with this playing quietly in the background? And what time is it for you at this exact moment? It's an oddly fitting question, because the very signals carrying this sound to you are themselves guided by electromagnetic fields, travelling invisibly across space until they reach you. Even this shared moment depends on the topic we're about to explore. If you find this kind of slow, thoughtful exploration comforting or interesting, and if it helps you unwind or focus or simply feel a little more curious about the world, you're welcome to like the video or subscribe to the channel. It helps this calm corner of science reach others who might enjoy it too. There's no rush. We're not going anywhere quickly tonight. Now, to begin making sense of electromagnetic fields, it helps to let go of the idea that science always starts with neat definitions and finished theories. Most of the time, understanding begins with small observations that don't quite fit together yet. A strange behaviour, a pattern noticed and then dismissed, then noticed again. Electromagnetic fields entered human knowledge this way, not as a single discovery, but as a slow accumulation of questions that refuse to stay separate. Imagine standing in a quiet room with a magnet in your hand. There's nothing visibly connecting it to anything else, and yet if you bring it near a piece of metal, the metal moves. No strings, no contact, no obvious mechanism. Something is happening across empty space. For centuries, this kind of action at a distance felt deeply uncomfortable to scientists and philosophers alike. How could one object affect another without touching it? What was carrying the influence? Electricity posed a similar puzzle. Rub amber with fur, and it attracts small bits of straw. Early thinkers noticed this thousands of years ago, but for a very long time, it remained a curiosity rather than a coherent concept. There was no sense yet that electricity and magnetism were related, let alone that they were two sides of the same phenomenon. They seemed like separate tricks of nature, each odd in its own way. The idea of a field emerged as a way to make sense of this invisible influence. Instead of imagining objects reaching out across space to pull or push each other directly, scientists began to think of space itself as active. Not empty, not passive, but filled with something capable of carrying forces. A field isn't a thing you can hold or point to, but it's not nothing either. It's a way of describing how the presence of one object changes the space around it, setting the stage for interactions long before anything else arrives. This shift in thinking was subtle, but profound. It meant that the world wasn't just made of solid objects bouncing off each other like billiard balls. It meant that the space between objects mattered. It could store energy. It could transmit influence. It could have structure and behaviour of its own. Once that door was opened, a much richer picture of reality began to emerge. Electromagnetic fields, specifically, arise from electric charges and from changing magnetic conditions. Wherever there is an electric charge, there is an electric field extending outward from it. Wherever there is a magnet, there is a magnetic field surrounding it. And crucially, when electric charges move, they create magnetic fields, and when magnetic fields change, they create electric effects in return. This constant interplay is what binds electricity and magnetism together into a single framework. What's remarkable is how universal this framework turns out to be. Light itself is an electromagnetic phenomenon. Radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays are all variations of the same underlying process. They differ only in wavelength and energy, not in nature. When you warm your hands near a heater, when sunlight reaches your skin, when your phone connects to a network, you're interacting with different expressions of electromagnetic fields. Despite this, most of us move through life barely aware of them. They don't announce themselves. They don't demand attention. You can't see a Wi-Fi signal drifting through a room or watch an electric field wrap itself around a wire. And yet, remove electromagnetic fields from the picture and the familiar world collapses almost instantly. Chemistry would fail. Atoms would not hold together. There would be no stable matter, no light, no life as we know it. This is part of what makes electromagnetic fields such a compelling subject. They operate at every scale at once. They govern the structure of atoms and molecules. They shape planetary environments. They enable global communication. They influence biological systems. And they do all of this quietly without ever stepping into view. As we move forward, the goal isn't to overwhelm you with equations or technical jargon. Instead, we'll trace how these ideas developed, how scientists slowly learned to think in terms of fields rather than forces alone, and how that shift reshaped our understanding of the universe. We'll look at how electricity and magnetism were once separate mysteries, how they were eventually unified, and how that unification led directly to technologies that now feel ordinary, but would have seemed miraculous not so long ago. Along the way, we'll also touch on the ways electromagnetic fields interact with living systems, including our own bodies, and how modern life has filled our environment with artificial fields layered on top of the natural ones that have always been here. Not to provoke fear or exaggeration, but to understand what is known, what is measured, and what remains uncertain. For now, it's enough to recognize that you're already immersed in this invisible landscape. You're moving through it, breathing within it, and relying on it without effort. The story of electromagnetic fields is not a story about distant phenomena or abstract theory. It's a story about the hidden structure of the everyday world, about the forces that quietly organize matter and motion around you, moment by moment, whether you notice them or not. And with that awareness in place, it becomes easier to step back to the beginning, to a time when none of this was obvious, when electricity and magnetism were puzzles without a shared explanation, and when the idea that empty space itself could carry forces was still far from accepted. That's where the story naturally continues, not with answers yet, but with the first signs that something unseen was at work, shaping outcomes in ways no one could quite explain at the time. Long before anyone spoke about fields or waves or equations, there were moments when nature behaved in ways that felt quietly unsettling. Not dramatic enough to inspire panic, not obvious enough to demand immediate explanation, but strange enough to linger in the mind. Small effects that suggested something unseen was at work. These were the first clues, scattered across centuries, that the world contained forces operating beyond direct touch. One of the earliest of these clues came from something very ordinary: amber. If you take a piece of amber and rub it with fur or cloth, it begins to attract small bits of straw, feathers, or dust. This was noticed thousands of years ago. The ancient Greeks observed it and wrote about it. The word electricity itself eventually came from the Greek word for amber, electron. But for a very long time, this was simply a curiosity. Amber had a trick. No one knew why. It didn't fit neatly into the way people understood motion or matter at the time. What made this phenomenon unsettling was that nothing visible seemed to connect the amber to the objects it attracted. There were no threads, no air currents, no contact, and yet something crossed the empty space between them. For most early thinkers, empty space was just that: empty. Nothing should happen there. Influence was expected to travel through contact, through pushing or pulling directly. Amber challenged that expectation in a quiet way. Magnetism produced a similar discomfort. Lodestones, naturally magnetized pieces of iron ore, were known in ancient China, Greece, and other cultures. Bring a lodestone near iron, and the iron moves. Bring two lodestones near each other, and they either attract or repel. Again, no visible cause. Again, an effect across space. Compasses, which rely on this behavior, became essential tools for navigation long before anyone understood why they worked. Sailors trusted them without needing to know the mechanism. North was north, and the needle knew where it was. These early experiences planted an idea that would take centuries to mature. There seemed to be influences in nature that did not require physical contact. Forces that reached out through space and produced consistent, repeatable effects. At first, these were treated as isolated oddities. Magnetism was one thing, static electricity was another. Lightning was something else entirely, often treated as divine or supernatural. There was no reason yet to connect them. As scientific thinking slowly became more systematic, especially during the Renaissance and early modern period, curiosity about these phenomena grew. People began to experiment deliberately rather than just observe passively. They rubbed materials together, suspended needles, floated iron filings, and watched what happened. Patterns began to emerge. One of the most telling moments came when people realized that magnetism seemed to organize space around it. Sprinkle iron filings around a magnet, and they don't arrange themselves randomly. They trace out smooth curves, arching from one end of the magnet to the other. These patterns are striking even today. They suggest structure where none was visible before. The filings appear to be following invisible paths, responding to something present in the space itself. At the time, no one would have called these paths fields. That concept hadn't been formalized yet, but the visual evidence was hard to ignore. Whatever magnetism was, it didn't just exist inside the magnet. It extended outward. It shaped the region around it. The magnet was not acting alone. Its influence filled the surrounding space. Electric effects, though harder to visualize, hinted at the same idea. When charged objects attracted or repelled one another, the effect wasn't random. It depended on distance. It depended on orientation. It followed rules, even if those rules were not yet known. Objects didn't simply snap together. They accelerated smoothly. Something was guiding their motion. This growing sense that space itself played an active role was deeply uncomfortable for many thinkers. Isaac Newton, who would later revolutionize physics in other ways, was famously uneasy with the idea of action at a distance. He accepted gravitational attraction mathematically because it worked, but he resisted explaining how it acted across empty space. The mechanism bothered him. The same discomfort applied to electricity and magnetism. For a long time, the preferred approach was to imagine hidden particles or fluids carrying forces between objects. Electricity was sometimes described as a fluid that flowed from one place to another. Magnetism was sometimes imagined as tiny currents circulating inside materials. These ideas were not entirely wrong, but they were incomplete. They tried to preserve the notion that something tangible was doing the work, even if it couldn't be seen directly. As experiments became more precise, the limitations of these explanations became clearer. Electrical effects could occur in vacuum. Magnetism did not weaken or strengthen in ways that simple fluid models predicted. The behavior was consistent, predictable, and resistant to being explained away as coincidence or illusion. One especially important realization was that electric and magnetic effects were directional. They didn't just depend on how far apart objects were, but also on how they were oriented. A compass needle aligns itself in a specific direction. A charged object influences other charges differently depending on their position. This directional quality suggested structure, not just force. Gradually, the language of science began to shift. Instead of asking how objects pulled on each other across space, some thinkers began asking what was happening in the space itself. What if space wasn't passive? What if it could carry information about forces? What if it could be altered by the presence of charges and magnets, and that alteration was what guided motion? This was a subtle but crucial change. It allowed scientists to stop worrying about how an object reached across emptiness and start focusing on local effects. Instead of imagining a magnet pulling iron directly, they could imagine the magnet changing the space around it, and the iron responding to the conditions in its immediate surroundings. Influence no longer had to leap across gaps, it could flow continuously through space. This idea didn't arrive all at once, and it wasn't immediately accepted. It took repeated experiments, careful observation, and a willingness to let go of older intuitions. But once it took hold, it opened the door to a far more unified understanding of nature. One of the strongest early clues that electricity and magnetism were related came from motion. Static electricity was one thing. Magnetism seemed stable and permanent. But when electric charges began to move, strange things happened. Wires carrying electric currents were found to influence compass needles. A current could deflect a magnet. This was unexpected. Electricity, which had been thought of as a separate phenomenon, was now interfering with magnetism. This single observation changed everything. It suggested that magnetism was not just a property of certain materials, but something that could be generated by electric motion. Electricity and magnetism were no longer isolated curiosities. They were interacting, and if they interacted, there was likely a deeper connection waiting to be uncovered. At this stage, the concept of a field became not just useful, but necessary. A moving electric charge didn't need to touch a compass needle to affect it. It changed the space around the wire, and the needle responded to that change. The influence was local, continuous, and directional. It behaved exactly as a field should. What's striking about this period is how cautious progress was. There were no grand declarations at first, no sudden announcements that the invisible world had been mapped. Instead, there was a growing accumulation of evidence that something consistent and real existed beyond direct perception. Each experiment added weight. Each successful prediction reinforced the idea that these unseen influences followed rules. This is an important point, because it highlights something fundamental about how science works. Discovery doesn't always begin with bold theories. Often, it begins with discomfort, with observations that don't fit comfortably into existing frameworks, with the nagging sense that something important is missing from the picture. Electromagnetic fields began as that missing piece. They weren't invented to sound impressive or abstract. They were introduced because nothing else could adequately explain what was being observed. They allowed scientists to describe how forces behaved without relying on imaginary fluids or instantaneous action at a distance. Once the idea of a field was accepted, even tentatively, it began to unify many loose ends. The strange behavior of magnets, the attraction and repulsion of charges, the effects of electric currents, all became different expressions of the same underlying structure. Space shaped by charges and currents guided matter along predictable paths. At the time, no one yet realised just how far this idea would reach. There was no reason to suspect that light itself was involved, or that radio waves, X-rays, and modern communication would one day fall under the same umbrella. Those connections would come later. For now, the important thing was simply acknowledging that something real, measurable, and invisible filled the space around us. This acknowledgement marked a turning point. Once scientists accepted that invisible influences could exist independently of objects, they gained a powerful new way to think about the world. They could talk about conditions at a point in space, about how those conditions changed, and about how objects responded locally rather than magically. And while this shift may sound abstract, its consequences were anything but. It laid the groundwork for everything that followed. It allowed electricity and magnetism to be studied systematically. It made it possible to predict outcomes before experiments were performed. It transformed curiosities into a coherent field of study. What began as amber attracting straw and stones pointing north slowly evolved into a recognition that the universe is filled with structured, invisible forces. Forces that don't announce themselves loudly, but that leave consistent traces for those willing to look carefully. These were the first clues, not yet fully understood, but impossible to ignore. As the evidence accumulated, it became clear that these influences were not rare exceptions or special tricks of nature. They were everywhere. They were woven into the fabric of ordinary experience. The challenge now was to understand their rules, their origins, and their full implications. And that challenge naturally leads forward, because once something unseen is acknowledged, the next question is unavoidable. If these invisible influences exist, what exactly are they made of? Where do they come from? And how do they arise from something as simple as electric charge? That question would soon become the focus of deeper investigation, guiding attention away from isolated effects and toward the underlying structure that produces them. To understand how electromagnetic fields come into being, everything has to slow down and return to a single, deceptively simple idea: electric charge. Before fields, before waves, before technology, there is charge. Not as a metaphor, not as an abstract label, but as a real measurable property of matter that quietly governs how particles interact with one another and with the space around them. Electric charge is one of the most fundamental attributes in physics. It does not depend on motion, shape, or size. A particle either has charge or it does not, and if it does, that charge has a specific value and sign, positive or negative. There is no halfway version, no gradual fading. Charge comes in discrete amounts, and every charged particle in the universe carries exactly the same basic unit, scaled up or down by whole numbers. This alone hints that something deeply structural is at work. Long before anyone understood atoms or subatomic particles, people encountered charge through friction. Rub two materials together and something strange happens. Lightweight objects begin to move, hair stands on end, tiny sparks jump through the air. These effects feel minor, almost playful, but they reveal an essential truth. Charge can be transferred. It can move from one object to another, even when nothing visible appears to change. For centuries, this behavior was treated as a surface phenomenon, a kind of trick caused by rubbing or contact. But as experimentation improved, patterns emerged. Some materials gained what we now call positive charge. Others gained negative charge, like charges repelled, unlike charges attracted. These rules were consistent, repeatable, and independent of scale. The same patterns appeared whether the charges were carried by large objects or microscopic particles. This consistency forced a deeper question. How does a charged object influence another object without touching it? The moment a piece of charged amber attracts straw across empty space, the idea of electric charge stops being just a property of matter and becomes something more. It becomes a source, a source of influence. At first, it was tempting to imagine charge as something that directly reached out and pulled on other charges, but this explanation quickly ran into trouble. The force depended on distance. It weakened smoothly as objects moved apart. It acted in specific directions, and it responded instantly to changes in position. These behaviors suggested organization, not random pulling. The breakthrough came when scientists began treating charge not just as something objects possessed, but as something that altered the space around them. A charged particle does not merely wait to interact when something comes close. It actively shapes its surroundings. It creates conditions in space that other charges respond to. Those conditions are what we call an electric field. An electric field is not a physical substance. You cannot scoop it up or store it in a container, but it is no less real for that. It has measurable strength. It has direction. It carries energy. And it exists whether or not another charge is present to feel it. This last point is crucial. The field is not created by interaction. It exists because the charge exists. Imagine placing a single charge particle in otherwise empty space. Nothing else is there. No test charge. No measuring device. According to the field concept, the space around that particle is still altered. If another charge were to enter that region, it would experience a force immediately, not because the original charge suddenly reached out, but because the space it entered was already structured. This idea resolves the discomfort of action at a distance. Forces no longer leap mysteriously across space. They are mediated locally. Each charge responds only to the conditions at its own position. The field carries the influence. Space becomes an active participant. Once this way of thinking took hold, electric interactions became far easier to describe and predict. Instead of tracking complex pairwise forces between every charged object, scientists could describe a field everywhere in space and then calculate how any charge would move within it. This shift was not just conceptual, it was practical. It simplified calculations and revealed symmetries that were invisible before. Electric fields have a clear structure. At any point in space, the field has a direction, defined as the direction a positive test charge would move if placed there. It also has a magnitude indicating how strong that push or pull would be. These two pieces of information together fully describe the field at that location. Visualizing this structure helped enormously. Early scientists used imagined lines, later called field lines, to represent the direction and relative strength of electric fields. These lines do not physically exist, but they are powerful tools for understanding behavior. They begin on positive charges and end on negative charges. Where the lines are dense, the field is strong. Where they spread out, the field weakens. What mattered was not the drawing itself, but what it represented. The field filled space continuously. There were no gaps, no sudden jumps. Influence flowed smoothly from one region to the next. This matched experimental observation far better than any picture of direct pulling ever had. Electric charge also introduced a new way of thinking about energy. When charges are arranged in an electric field, energy is stored in that configuration. Separate two opposite charges and you must do work. Bring them closer and energy is released. That energy does not vanish into the charges themselves. It resides in the field between them. This was a radical idea at the time. Energy stored in empty space sounded almost nonsensical at first, but experiments left a little room for doubt. Capacitors, devices that store energy using electric fields, made this reality unavoidable. Two metal plates separated by an insulator can hold energy without moving parts, without chemical reactions, simply because of the electric field between them. Remove the field, and the energy is gone. This realization marked the true birth of fields as physical entities rather than mathematical conveniences. Fields could store energy. They could transfer energy. They could change over time. They could exist independently of matter, though always sourced by it. Once this door opened, there was no going back. Charge itself turned out to be even more fundamental than originally imagined. With the discovery of the electron, it became clear that negative charge was carried by a specific particle present in all atoms. Positive charge resided in atomic nuclei. Electric interactions were not surface effects at all. They were rooted in the structure of matter. Atoms, once thought indivisible, were revealed as dynamic systems held together by electric forces. Electrons remain bound to nuclei not because of glue or hooks, but because of electric fields. Chemical bonds, the basis of all chemistry and biology, are rearrangements of electric charge and fields. The solidity of objects, the resistance you feel when you press your hand against a table, arises largely from electric repulsion between electrons. At this point, it becomes clear that electric fields are not secondary features of the universe. They are central. Without them, matter would not have structure. Atoms would not form. Molecules would not exist. There would be no stable objects, no light, no life. What makes electric fields especially interesting is how they respond to change. A static charge produces a static field. But when charges move, when currents flow, the situation becomes richer. Fields shift, rearrange, propagate. Changes in electric fields do not remain local. They spread outward through space. This spreading does not happen instantaneously. It travels at a finite speed. That speed, as later discovered, is the speed of light. This single fact would eventually connect electricity, magnetism, and light into a unified framework, but even before that connection was made, it hinted that electric fields were capable of independent behaviour. They were not merely bookkeeping devices, they had dynamics. Another critical realization was that fields exert forces not only on charges, but also on other fields. Electric fields interact with magnetic fields. They influence each other's structure and evolution. This mutual influence would eventually lead to the concept of electromagnetic fields as a single entity rather than two separate ones. But at the stage where electric charge gave birth to fields, the most important lesson was simpler. Space is not passive. Place a charge somewhere, and space itself changes. That change persists. It can be measured. It can do work. And it provides the mechanism through which all electric interactions occur. This way of thinking quietly reshaped physics. It shifted attention away from objects alone and toward relationships, away from isolated particles and toward the conditions they create around themselves. It made local behaviour central and eliminated the need for mysterious long-range pulls. Even today, this perspective underlies everything from basic circuit design to advanced theoretical physics. Engineers design devices by shaping electric fields. Physicists describe interactions by writing equations for how fields behave. Chemists understand reactions by tracking charge distributions. Biologists study nerve impulses as waves of electric potential moving through tissue. And yet, for all its importance, the electric field remains invisible. You cannot see it directly. You infer its presence through motion, through force, through energy. It reveals itself only through its effects. That invisibility is not a flaw. It is a feature. It allows the same framework to apply everywhere, from the smallest scales to the largest. Once electric charge was understood as a source of fields rather than a self-contained actor, a new question naturally followed. If electric fields arise from charge, and if moving charges produce new effects, then what exactly is the relationship between electricity and magnetism? Why does a flowing current influence a compass needle? Why does motion matter at all? Those questions did not arise from speculation. They arose from observation, from wires deflecting needles, from experiments that refused to stay neatly categorized. And answering them would require extending the idea of fields even further, beyond static charges and into the dynamic interplay that defines the electromagnetic world. Long before electricity was understood, before charge was named, counted, or tracked through wires, magnetism stood on its own as a quiet, stubborn mystery. It did not announce itself with sparks or shocks. It did not require rubbing or friction. It simply existed, steady and persistent, revealing itself through orientation rather than motion, through alignment rather than attraction alone. In many ways, magnetism was humanity's first sustained encounter with an invisible force that behaved with purpose. The earliest known magnetic materials were lodestones, naturally magnetized pieces of iron-rich rock. These stones were not manufactured or engineered. They were found. Pick one up, bring it near iron, and the iron moved. Not randomly, not reluctantly, but decisively. Even more curious, a lodestone suspended freely would rotate until it pointed in a consistent direction. No matter where you were, no matter who held it, the stone seemed to know something about the world that people did not. This behaviour was noticed independently in different parts of the world. In ancient China, magnetized needles were used for divination before they were used for navigation. In Greece, thinkers like Thales of Miletus remarked on the strange properties of lodestones, noting that they seemed to possess a kind of life because of their ability to move iron. The language used at the time was telling. Magnetism was often described in animate terms, as if the stone had intention. Unlike electrical effects, which came and went depending on conditions, magnetism felt permanent. A lodestone did not lose its power after use. It did not need to be recharged by friction. Its influence was always present. This made it especially puzzling. Whatever caused magnetism appeared to be locked into the material itself. The compass transformed magnetism from curiosity into necessity. Once people realized that a magnetized needle reliably aligned itself with the Earth, navigation changed permanently. Open sea travel became safer, trade expanded, exploration accelerated. All of this depended on a force no one could explain. What mattered most about the compass was not attraction or repulsion, but direction. Magnetism did not merely pull things together, it imposed orientation. A compass needle did not rush toward the north, it turned and settled. This behaviour hinted that magnetism was less about force in the usual sense, and more about structure. Something about space itself seemed organised. For centuries, magnetism resisted integration into existing frameworks. Aristotelian physics had little to say about it. Mechanical explanations struggled. Some proposed that magnets emitted invisible vapours or streams that latched onto iron. Others imagined tiny hooks or threads connecting materials. None of these ideas fully captured the observed behaviour, especially the directional nature of magnetic effects. The Earth itself added another layer of complexity. The fact that a compass needle aligned with the planet suggested that magnetism operated on a global scale. This was not a local trick of certain stones, it was something embedded in the world. The Earth behaved like a giant magnet, though no one yet understood how or why. One of the most revealing experiments involved iron filings. When sprinkled around a magnet, the filings arranged themselves into smooth, curved patterns. These patterns were not arbitrary. They traced arcs from one end of the magnet to the other. They revealed symmetry, they revealed order, and they did so in a way that no verbal explanation could easily dismiss. These patterns implied that magnetism was not confined to the magnet itself. The space around the magnet mattered. It had structure. It guided motion. The filings were not being pulled directly by the magnet in a straight line. They were responding to conditions at their own location, aligning themselves along invisible pathways. At the time, there was no language for this beyond metaphor, but the implication was clear. Magnetism filled space. It was not an isolated property. It extended outward, shaping the environment around magnetic objects. Another defining feature of magnetism was polarity. Every magnet had two ends, later called north and south. These poles could not be separated. Break a magnet in half, and each piece still had a north and a south. This behaviour was deeply unlike electric charge, which could be isolated. You could have a positively charged object or a negatively charged one. But magnetism always came in pairs. This indivisibility frustrated early attempts to reduce magnetism to simpler components. If magnetism were caused by a fluid, why couldn't it be split? If it were caused by particles, why were they inseparable? The persistence of paired poles suggested that magnetism was not a substance that could be divided at will. Even more strangely, like poles repelled while opposite poles attracted. This symmetry was elegant, but it raised questions. Why should the universe care about orientation in this way? Why should space distinguish between north and south? Magnetism also displayed sensitivity to geometry. The strength of a magnetic effect depended not just on distance, but on alignment. Rotate a magnet relative to an object, and the behavior changed. This dependence on orientation hinted at something more complex than simple attraction. By the early modern period, systematic study of magnetism began to emerge. William Gilbert, an English physician, published one of the first comprehensive works on magnetism in 1600. He proposed that the Earth itself was a magnet, and that compass needles aligned with its field. This was a bold claim, and it reframed magnetism as a planetary phenomenon rather than a local curiosity. Gilbert's work also helped separate magnetism from superstition. He argued that magnetic effects were natural and lawful, not mystical. This shift mattered. It allowed magnetism to enter the realm of experimental science. Still, magnetism remained isolated conceptually. Electricity, when it was studied, was treated as something entirely different. Electrical effects were often transient, explosive, and associated with friction or lightning. Magnetism was steady, directional, and embedded in materials. There was no obvious reason to connect them. The separation persisted partly because magnetism did not require motion. A stationary magnet exerted influence. Nothing needed to flow. Electricity, by contrast, seemed to involve transfer. Sparks jumped. Charges moved. The two phenomena appeared fundamentally different. Yet beneath this apparent difference, magnetism was quietly laying the groundwork for a deeper understanding. Its insistence on spatial structure, on orientation, on paired behavior, all pointed toward a framework that would later become essential. Magnetism demanded that space be taken seriously. Even the language surrounding magnetism reflected this. People spoke of magnetic influence rather than magnetic force, of lines, directions, and tendencies rather than pushes and pulls. These intuitions, though informal, were closer to the truth than many realized at the time. What magnetism lacked was a connection to something more familiar. It needed a bridge. That bridge would come not from magnets themselves, but from motion, from currents, from electricity beginning to flow in controlled ways. But before that connection was made, magnetism existed as a complete mystery in its own right. It guided ships across oceans. It aligned needles in quiet rooms. It shaped patterns in iron filings. And it did all of this without revealing its source. This long period, when magnetism stood alone without electricity, was not a dead end. It was a preparation. It trained scientists to accept invisible structure. It forced them to consider space as active. It introduced the idea that influence could be directional, extended, and inseparable from geometry. By the time electricity began to be understood more clearly, magnetism was already waiting, with its patterns drawn and its rules quietly established. The moment motion entered the picture, the moment charges began to move through wires, the separation between these two phenomena would no longer hold. And when that happened, magnetism would no longer be a standalone mystery. It would become part of something larger, something unified, something that would finally explain why a compass needle turns when a current flows nearby, and why electricity and magnetism were never truly separate to begin with. For a long time, electricity and magnetism lived in separate intellectual rooms. They were studied by different people, explained with different language, and associated with different kinds of phenomena. Electricity sparked, shocked, and leapt. Magnetism aligned, oriented and quietly persisted. There was no obvious reason to think they were related, and for years no experiment forced that connection into view. When the meeting finally happened, it was not dramatic in the way we often imagine scientific revolutions. It was subtle, almost accidental, and yet it changed everything. The moment came not from theory, but from curiosity. In the early 19th century, scientists were learning how to produce steady electric currents rather than brief static discharges. Volta's invention of the battery made it possible to send electricity through wires continuously. This alone was a major shift. Electricity was no longer a fleeting effect. It could flow, be controlled, sustained, and observed over time. Once currents became reliable, people began placing wires in different configurations, connecting them to metal plates, coils, and measuring devices, and watching what happened. Many of these experiments were exploratory rather than targeted. The goal was not always to test a specific hypothesis, but to see what electricity might do under new conditions. In 1820, during one such demonstration, a Danish physicist named Hans Christian Ørsted noticed something unexpected. A compass needle placed near a current-carrying wire deflected from its usual north-south alignment. When the current was switched off, the needle returned to its original position. When the current flowed again, the needle moved again. The effect was immediate and repeatable. This observation was quietly shocking. A flowing electric current was influencing a magnet, not heating it, not charging it, but altering its orientation. Electricity, it seemed, could produce magnetic effects. At first glance, this might not seem earth-shattering, but within the context of the time, it was profound. Magnetism had always appeared as a static property of certain materials or of the Earth itself. Here, magnetism was being generated by motion, by electricity in transit. The details mattered. The magnetic effect did not radiate outward uniformly like an explosion. It wrapped itself around the wire. The compass needle did not point toward the wire. It aligned itself tangentially, as if tracing a circle around it. This behavior was strange and deeply informative. What it revealed was that magnetic influence had a rotational character. It did not point directly at its source. It curved. It formed loops. This was entirely unlike the straight-line attraction and repulsion familiar from static electric charges. Very quickly, other scientists began repeating and extending these experiments. André-Marie Ampère in France explored the forces between current-carrying wires and discovered that two parallel currents attract or repel each other depending on the direction of flow. Electricity in motion could generate forces not just on magnets, but on other electric currents. This was a turning point. Magnetism was no longer confined to special stones or planetary effects. It could be created on demand. Turn the current on, magnetism appears. Turn it off, magnetism disappears. This controllability was unprecedented. The implications were enormous. If electricity could generate magnetism, then magnetism might be nothing more than electricity in motion. This idea was not immediately obvious, but it began to take shape as experiments piled up. Once again, the concept of a field became indispensable. A current-carrying wire did not simply tug on a compass needle at a distance, it altered the space around it. That altered space guided the needle's orientation. The magnetic field around the wire formed closed loops, encircling the current. This circular structure was not decorative, it was essential. It explained why reversing the direction of the current reversed the direction of the magnetic effect. It explained why the compass needle behaved the way it did. The field carried the information. What made this especially important was that magnetism no longer needed permanent magnets. It could arise dynamically from moving charges. This reframed magnetism as a consequence rather than a primitive phenomenon. Soon the reverse question became unavoidable. If electricity could produce magnetism, could magnetism produce electricity? This question did not remain hypothetical for long. Michael Faraday, working in England, took it seriously. Faraday was not a mathematician by training. He thought in terms of experiments, apparatus, and physical intuition. He imagined fields not as abstract constructs, but as real structures in space. Faraday discovered that changing magnetic conditions could induce electric currents. Move a magnet near a coil of wire, and a current appears. Hold the magnet still, and nothing happens. Move it again, and the current returns. The key was change. This phenomenon, electromagnetic induction, completed the loop. Electricity could produce magnetism. Magnetism, when changing, could produce electricity. The two were locked together in a reciprocal relationship. This was not just a connection, it was a unification. Electricity and magnetism were no longer separate effects that happened to interact. They were aspects of the same underlying process. Motion and change were the bridge. The field concept now expanded dramatically. Electric fields and magnetic fields were no longer static backgrounds. They were dynamic. They could evolve, influence each other, and propagate through space. Faraday's experiments also reinforced the idea that fields were real physical entities. The effects did not depend on contact or direct force transmission. They depended on the state of space itself. Change the field, and matter responds. At this stage, the language of physics began to shift permanently. Scientists no longer spoke only of charges and currents. They spoke of fields filling space, carrying energy, and guiding motion. The field was not just a convenient model, it was the primary actor. One of the most surprising consequences of this unification was the realization that electromagnetic effects could exist even without charges present. Changing fields could sustain themselves, propagating outward through space as waves. This idea was still years away from full articulation, but its seeds were already planted. The meeting of electricity and magnetism also changed how energy was understood. Energy was no longer confined to matter or motion. It could reside in fields. It could move through empty space. This would later explain how light travels from the sun to Earth without a medium. But even before those grand conclusions, the practical consequences were immediate. Electric motors, generators, and transformers became possible. Motion could be converted into electricity. Electricity could be converted into motion. This feedback loop powered the modern world. Yet at the moment of discovery, the atmosphere was quieter. There was no sense of finality. Each answer raised new questions. What exactly were these fields? How fast did changes propagate? Why did magnetic fields curve? Why did electric and magnetic effects seem inseparable once motion entered the picture? Those questions demanded a deeper framework. Experiments had revealed the connection, but they had not yet explained it fully. The patterns were clear, but the underlying rules were still being assembled. What was certain now was that electricity and magnetism could no longer be treated as separate topics. They were two faces of a single phenomenon, a phenomenon rooted in charge, motion, and the structure of space itself. From here, the task was no longer to observe isolated effects, but to describe the whole system coherently, to find the principles that governed how fields formed, changed, and interacted. That work would soon fall to those who could translate Faraday's physical intuition into precise mathematical language, revealing just how deeply unified these invisible forces truly were. By the time electricity and magnetism were known to influence one another, science had reached an awkward but fertile stage. Experiments were producing reliable, repeatable results, but the conceptual language lagged behind. People could describe what happened, but not always why it happened in a satisfying way. This gap was especially noticeable in the early 19th century, when equations existed for forces between charges and currents, yet those equations did little to explain the underlying structure tying everything together. Into this gap stepped Michael Faraday, bringing with him a way of thinking that would quietly transform physics. Faraday did not approach nature through mathematics first. His background was practical, experimental, and deeply visual. He cared less about manipulating symbols and more about understanding how phenomena behaved in real space. Where others saw forces acting between objects, Faraday saw patterns forming in the space around them. This difference in perspective would prove decisive. One of Faraday's most enduring contributions was his insistence that electric and magnetic effects were not transmitted instantaneously or mysteriously from object to object. Instead, he argued that these effects were carried by something present everywhere in between. He called this something lines of force. Today we call them field lines, but the original idea was richer than the diagrams that later textbooks would reduce them to. Faraday's lines were not imaginary arrows drawn for convenience. To him, they represented the actual state of space. When a magnet sat on a table, Faraday did not think of it as pulling iron filings toward itself across emptiness. He thought of the magnet as altering the surrounding space, filling it with a structured pattern that the filings simply followed. The filings were not responding to the magnet directly. They were responding to the local conditions where they sat. This way of thinking was radical at the time. Many physicists still preferred action at a distance explanations, where forces jumped across space without delay or mediation. Fields, to them, felt like unnecessary complications. Faraday disagreed. He believed that if an effect was observed at a location, then something physically meaningful must be present there to cause it. The iron filings experiments became central to this view. When sprinkled around a magnet, the filings traced out smooth, continuous curves. These curves were not decorative. They revealed the geometry of magnetic influence. They showed where the influence was strong and where it weakened. They showed that magnetism did not radiate outward evenly, but followed specific paths. Faraday noticed that these lines never crossed. They curved gracefully, forming closed loops that connected one end of a magnet to the other. This observation hinted at a deeper rule. Magnetic influence did not begin or end in empty space. It was continuous. Even without knowing why, Faraday understood that magnetism behaved differently from electricity, which could begin and end on charges. Electric fields, too, could be visualized in terms of lines. Place charged objects in space, and Faraday imagined lines stretching outward, indicating the direction a test charge would move. These electric lines began on positive charges and ended on negative ones. Where they were dense, the electric effect was strong. Where they spread out, it weakened. What mattered was not the lines themselves, but what they encoded: direction, strength, continuity. Fields were no longer abstract forces acting between objects. They were structured environments that existed independently of whether anything was there to experience them. Faraday's intuition extended naturally to time. If fields existed in space, then changes in those fields should take time to propagate. This idea contradicted older assumptions that forces acted instantaneously. Faraday suspected that when a charge moved or a magnet shifted, the surrounding field did not update everywhere at once. Instead, the change travelled outward. At the time, this was speculation. There was no direct way to measure the speed of such changes, but the idea itself was powerful. It suggested that electromagnetic effects were local and causal, not instantaneous and mysterious. It suggested that space itself had physical properties that could change. Faraday's work on electromagnetic induction reinforced this picture. When a magnetic field through a loop of wire changed, an electric current appeared in the wire. Importantly, the current depended on the rate of change, not simply the presence of the field. A steady field did nothing. A changing field produced motion. This behavior fit perfectly with the field picture. The magnetic field was not a static background. It was an active entity. When it changed, it created new conditions in space, and those conditions produced electric effects. Faraday visualized this process using his lines. As a magnet moved relative to a conductor, the magnetic lines swept across the wire. Their motion was not symbolic. It was the mechanism. The crossing of lines corresponded to induced current. Many of Faraday's contemporaries were uneasy with this language. Lines sounded metaphorical. They wanted equations. They wanted forces between particles. But Faraday's experiments kept working. His predictions held. The field picture, whether others liked it or not, matched reality. One of the most subtle but important aspects of Faraday's thinking was that fields carried energy. When you move a charge in an electric field, you do work. That work does not vanish. It changes the energy stored in the field itself. The same is true for magnetic fields. Energy is distributed throughout space, not locked inside objects. This idea challenged deeply held assumptions. Energy had traditionally been associated with motion or position of material bodies. The notion that empty space could store energy felt unsettling. But again, experiments left little room for doubt. Devices like inductors and capacitors behaved exactly as the field picture predicted. Faraday also recognized that electric and magnetic fields were not independent actors. They were aspects of a single system. A changing electric field produced a magnetic effect. A changing magnetic field produced an electric effect. The lines of force were not static drawings. They were dynamic structures, capable of evolving over time. This dynamism hinted at something even more profound. If fields could change and induce each other, then under the right conditions they might sustain themselves. A disturbance in the field could propagate outward without requiring charges or currents to follow along. In other words, a wave. Faraday did not fully formalize this idea, but he sensed its possibility. He suspected that light itself might be a manifestation of electromagnetic activity. This was an extraordinary leap of intuition, made without the mathematical tools needed to prove it. Still, the idea lingered. What made Faraday's contribution so enduring was not just any single discovery, but the framework he introduced. He taught science to look at space differently, to treat it as something with structure, capable of holding energy and transmitting influence, to stop asking how objects reach across space and start asking what space is doing locally. This shift had consequences beyond electromagnetism. It influenced how gravity would later be understood. It influenced how waves, radiation, and even modern field theories would develop. The idea that fundamental interactions are mediated by fields rather than direct contact is now foundational. At the time, however, Faraday's work remained incomplete in the eyes of many. His descriptions were rich but qualitative. They lacked the mathematical precision that 19th century physics increasingly demanded. The challenge now was to translate his physical insight into equations without losing its essence. That task would fall to someone else, someone who could take Faraday's invisible lines and show that they were not just helpful pictures, but inevitable consequences of deeper laws. Someone who could demonstrate that once the field idea was accepted, everything else followed logically. Faraday had revealed the shape of the invisible. He had shown that electric and magnetic effects were not scattered tricks, but organized patterns filling space. What remained was to express those patterns in a form that could be tested, extended, and unified completely. And as the lines of force curved and looped through space in Faraday's imagination, they quietly prepared the way for a mathematical framework that would bind electricity, magnetism, and light into a single, coherent picture of the world, one that would soon show just how far these invisible structures really extend. By the time Michael Faraday had finished his experimental work, the pieces of the larger picture were clearly present, but they were scattered. Electricity and magnetism had been shown to interact. Fields had been revealed as real structures filling space. Change, not mere presence, had been identified as the key to induction. What was still missing was a single framework that could hold all of this together without contradiction, ambiguity, or reliance on intuition alone. That framework would emerge quietly through the work of one person who never performed a dramatic public experiment and never imagined lines of force as physical threads in space, but who understood, perhaps better than anyone else of his time, how to translate physical insight into mathematical structure. James Clerk Maxwell approached electromagnetism from a very different direction than Faraday. Where Faraday thought visually and experimentally, Maxwell thought structurally and mathematically. Yet what makes his contribution remarkable is that he did not discard Faraday's ideas. Instead, he took them seriously in a way few others had. He asked a simple but profound question. If Faraday's fields are real, what equations must they obey? At first glance, this might sound like a technical exercise, but it was much more than that. Writing equations for fields required committing to the idea that the fields themselves were fundamental objects, not just convenient summaries of forces between particles. Maxwell accepted this fully. He treated electric and magnetic fields as continuous entities defined at every point in space and time, capable of changing, interacting, and carrying energy. Maxwell began by collecting what was already known. There were laws describing how electric charges produced electric effects. There were laws describing how currents produced magnetic effects. There were experimental rules governing induction. Each worked well in its own domain, but they did not yet form a coherent whole. Maxwell's task was not to invent entirely new physics, but to see how these pieces fit together. One of the first insights was that electric fields originate from electric charge. This relationship could be expressed cleanly and locally. At any point in space, the divergence of the electric field depended on how much charge was present there. This captured, in precise form, the idea that electric fields begin and end on charges. Magnetism, however, behaved differently. Magnetic fields did not originate from isolated magnetic charges. No matter how deeply scientists looked, they never found a single magnetic pole by itself. Magnetic influence always formed closed loops. Maxwell encoded this directly into his equations by stating that the divergence of the magnetic field is zero everywhere. This was not an assumption. It was a summary of all experimental evidence available. These two statements alone already reflected Faraday's intuition about field structure, but Maxwell did not stop there. The real unification came when he examined how fields changed over time. It was already known that a changing magnetic field could induce an electric current. Faraday had demonstrated this repeatedly. Maxwell translated this into an equation stating that the curl of the electric field depends on how the magnetic field changes with time. This captured induction not as a mysterious effect, but as a direct consequence of field dynamics. Up to this point, everything Maxwell wrote down corresponded closely to known experiments. Then came the bold step. Maxwell noticed an asymmetry. Electric currents produced magnetic fields, but the equation suggested that only actual currents, moving charges, could do this. Yet electric fields could also change over time, especially in situations like charging a capacitor, where no charge physically crossed the gap between plates. If a changing magnetic field could create an electric field, symmetry suggested that a changing electric field should create a magnetic effect as well. But no such term existed in the equations. The mathematics felt incomplete. Rather than dismiss this as a flaw in intuition, Maxwell took it seriously. He introduced an additional term, now known as the displacement current. This term did not represent the motion of charge through space. It represented the change of the electric field itself. According to Maxwell, a changing electric field was enough to produce magnetic effects, even in the absence of conduction current. This was a radical move. At the time, there was little direct experimental evidence for such an effect. But without it, the equations failed to conserve charge properly, and broke the symmetry that Faraday's ideas seemed to demand. Maxwell trusted the structure. With this addition, the picture snapped into place. Electric fields and magnetic fields were no longer separate actors that occasionally interacted. They were two aspects of a single, self-consistent system. Changes in one necessarily produced changes in the other. The fields were intertwined. When Maxwell examined the consequences of his equations, he found something extraordinary. If electric and magnetic fields could generate each other through time, then under the right conditions, they could propagate through space together as a coupled disturbance, a wave. By calculating the speed at which this disturbance would travel, Maxwell arrived at a familiar number. It matched the known speed of light. This was not a coincidence. It was a revelation. Light, Maxwell concluded, is an electromagnetic wave. This statement quietly unified vast domains of physics. Light was no longer a special substance or an ether vibration. It was an expression of the same fields produced by charges and currents. The glow of a candle, the warmth of the sun, the colours of the sky all became part of electromagnetism. This insight did not depend on new experiments. It emerged directly from the internal consistency of the equations. Once the field picture was taken seriously and completed symmetrically, light appeared inevitably. Maxwell's equations also clarified something that had been implicit but not fully appreciated. Electromagnetic influence does not travel instantaneously. Changes in fields propagate at a finite speed. When a charge moves, the surrounding field does not update everywhere at once. The change spreads outward through space. This resolved long-standing discomfort with action at distance. There was no need for instantaneous influence. Causality was preserved. Local changes produced local effects that travelled outward. Another consequence was the realization that electromagnetic fields carry momentum as well as energy. A beam of light can exert pressure. Radiation can push. Again, this was not philosophical speculation. It followed directly from the field equations. Maxwell's work also revealed that the electric and magnetic fields depend on the observer's frame of reference. What appears as a purely electric effect in one situation can appear as a combination of electric and magnetic effects in another. This hinted at a deeper unity that would later be explored more fully, but even at this stage it suggested that the separation between electricity and magnetism was not absolute. At first, Maxwell's work was not universally embraced. The mathematics was dense, the ideas were abstract. Many experimentalists were more comfortable with forces and circuits than with fields defined at every point in space. Faraday himself never fully engaged with Maxwell's equations, yet the predictive power was undeniable. Maxwell's framework explained known phenomena and predicted new ones. It unified static electricity, magnetism, induction, and light without contradiction. It reduced a messy collection of rules to a small set of principles. Over time, experiments confirmed the existence of electromagnetic waves beyond visible light. Radio waves were detected. Later, microwaves, infrared, ultraviolet, X-rays, and gamma rays followed. Each discovery fit neatly into Maxwell's picture. What made this unification so enduring was not just its scope, but its restraint. Maxwell did not introduce unnecessary assumptions. He did not speculate about the substance of fields. He described how they behave. That behavior turned out to be enough. In this picture, the universe is not filled with invisible fluids or instantaneous forces. It is filled with fields that evolve according to simple rules. Charges and currents shape those fields. The fields, in turn, guide matter and transmit energy. This way of thinking marked a turning point in physics. It showed that invisible structures could be just as real as solid objects. It demonstrated that unification was possible without oversimplification, and it revealed that the everyday world of light and electricity was governed by the same principles. Yet even Maxwell's picture was not the final word. His equations worked astonishingly well, but they contained a quiet tension. They implied a preferred speed for electromagnetic waves, a speed that seemed absolute. Reconciling that implication with motion and reference frames would require another shift in thinking. For now, though, Maxwell had given the invisible a clear and consistent form. He had shown that Faraday's lines were not just useful metaphors, but manifestations of deeper laws. Electricity and magnetism were no longer separate chapters in physics. They were a single story, written in the language of fields, unfolding continuously through space and time. And once that story existed, it became impossible to ignore its implications, because the same equations that described wires and magnets were quietly describing light itself, suggesting that the world was woven together by oscillations of fields that never needed matter to carry them forward. Once Maxwell's equations were written down in their complete form, something subtle but far-reaching became unavoidable. The equations did not merely describe static arrangements of charges and currents, or steady magnetic configurations frozen in place. They described how electric and magnetic fields change, and more importantly, they described how those changes do not stay where they begin. If an electric field changes in time, Maxwell's equations say that a magnetic field appears in response. If a magnetic field changes, an electric field appears in response. Neither effect requires matter to be present. Neither requires a wire, a charge drifting through metal, or a magnet being physically moved. Change alone is enough, and once change exists, it feeds back on itself. This mutual generation is the key to understanding electromagnetic waves. They are not objects launched from a source. They are not streams of particles flying through space, at least not in the everyday sense. They are self-sustaining patterns of change in the electromagnetic field itself. Imagine a region of space where an electric field begins to oscillate. Perhaps it is driven initially by an accelerating charge, such as an electron jostled inside an antenna. As the electric field changes, a magnetic field forms around it. That magnetic field, now changing in time, produces a new electric field slightly farther out. That new electric field produces another magnetic field, and so on. The disturbance moves outward, not because anything is being pushed, but because the field's own rules demand it. What is moving is not matter. What is moving is a pattern. This is a difficult idea to internalize because so much of everyday experience involves objects traveling from one place to another. A ball flies through the air. A car moves down a road. Sound travels because air molecules bump into one another. Electromagnetic waves do not work that way. Nothing needs to bump into anything else. There is no medium required. The fields themselves are the medium. This was one of the most radical implications of Maxwell's work. It meant that empty space was not truly empty. It could support waves. It could transmit energy and information without carrying matter along for the ride. At first, many physicists resisted this idea. The prevailing intuition was that waves must have something to wave. Water waves require water. Sound waves require air or another material. It seemed natural to assume that electromagnetic waves must also require a medium. This hypothetical substance was called the luminiferous ether, an invisible material thought to permeate all of space. The ether was imagined as incredibly stiff, to allow light to travel so fast yet completely undetectable by ordinary means. It did not resist motion. It did not drag planets. It existed only to give light something to vibrate in. For decades, physicists tried to make sense of this imagined medium. They debated its properties, proposed models, and attempted to detect motion relative to it. But experiment after experiment failed to reveal its presence. Light behaved the same regardless of the motion of its source or observer. The wave existed, but the medium did not. The eventual realization, difficult as it was, followed naturally from the field picture. Electromagnetic waves do not require a substance beneath them. They are oscillations of the field itself. The field is not a thing sitting inside space. It is part of what space is. Once this was accepted, the behavior of electromagnetic waves became much easier to describe. They propagate at a fixed speed, determined by the fundamental constants governing electric and magnetic interactions. That speed does not depend on the motion of the source. It does not depend on the environment. It is a property of the fields themselves. An electromagnetic wave consists of an electric field and a magnetic field oscillating in synchrony, perpendicular to each other and to the direction of travel. The electric field rises and falls. The magnetic field rises and falls. Neither exists alone. Each supports the other. This perpendicular structure is not arbitrary. It follows directly from Maxwell's equations. The direction of the electric field determines the direction of the magnetic field, and together they determine the direction the wave moves. Energy flows through space carried by this coupled motion. Despite their invisibility, electromagnetic waves transport real energy. When sunlight warms your skin, that energy is travelled across millions of kilometres of empty space carried entirely by oscillating fields. No particles were required to ferry it. No substance bridged the gap. The amount of energy carried by a wave depends on the strength of its fields. Stronger oscillations carry more energy. The frequency of oscillation determines the type of wave. Low-frequency waves have long wavelengths and gentle variations. High-frequency waves oscillate rapidly and carry more energy per unit. What we call radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays are all electromagnetic waves. They differ only in frequency and wavelength. There is no fundamental boundary separating them. The divisions are historical and practical, not physical. This continuity is one of the most elegant features of electromagnetism. A radio signal and a beam of visible light are manifestations of the same underlying process. One simply oscillates more slowly than the other. One interacts gently with matter. The other interacts strongly enough to excite atoms and trigger vision. Electromagnetic waves do not spread out uniformly in all situations. Their behaviour depends on how they are generated and how they encounter matter. They can reflect, refract, interfere, diffract, and scatter. All of these behaviours arise from how the fields respond to boundaries and changes in material properties. When a wave encounters a conductor, the electric field pushes charges around. Those charges rearrange in such a way that they produce their own fields, often cancelling the wave inside the material and reflecting it outward. This is why metals reflect light and radio waves so effectively. When a wave passes through an insulating material, the electric field causes charges within atoms to shift slightly. These shifts re-radiate the wave, slowing it down and bending its path. This is refraction. The wave is not absorbed and re-emitted as a new entity. It is continuously reshaped by its interaction with the medium. Interference occurs when multiple waves overlap. Because fields are together, regions of reinforcement and cancellation appear. This is not a property of particles. It is a property of waves. Light can brighten or darken itself depending on how its oscillations line up in space and time. Diffraction, the spreading of waves around obstacles and through openings, further emphasizes that electromagnetic waves are not beams traveling along rigid lines. They are extended structures sensitive to geometry, boundaries, and scale. All of these behaviors were well known in optics long before electromagnetism was unified. What Maxwell's picture provided was a single explanation for all of them. Reflection, refraction, interference, and diffraction were no longer special rules for light. They were natural consequences of field behavior. Perhaps the most important implication of electromagnetic waves is that they allow influence without contact. Information can be encoded into oscillations and transmitted across vast distances. This is not a side effect. It is a fundamental feature. Every wireless technology relies on this. A transmitter accelerates charges in a controlled way, generating oscillating fields. Those fields propagate outward as waves. A receiver placed within that field responds to the oscillations, extracting energy and information. The space between transmitter and receiver does not need to be filled with anything special. It does not need wires. It does not need air. It does not need line-of-sight particles. The fields do the work. This also means that electromagnetic waves do not weaken because they get tired or lose momentum. They weaken because they spread. As the wavefront expands, the same energy is distributed over a larger area. The fields become weaker, but the wave itself remains intact unless it interacts with matter. From a deeper perspective, Electromagnetic waves reveal something profound about the nature of reality. They show that change can propagate without substance. That structure can exist without material support. That energy can move without mass. They also hint at limits. Because electromagnetic waves travel at a fixed speed, they impose a maximum rate at which information can move. No signal carried by these fields can outrun that speed. This is not a technological limitation, it is a structural one. This limit would later force a rethinking of space and time themselves, but even within classical electromagnetism, it establishes a clear boundary between cause and effect. Changes propagate. They do not appear everywhere at once. Another subtle implication is that the separation between electric and magnetic fields depends on perspective. What appears as a purely electric oscillation in one frame of reference may appear as a mixture of electric and magnetic effects in another. The wave itself is invariant, but the way its components are described is not. This realization would eventually point toward a deeper unity, but at this stage, it was enough to recognize that electromagnetic waves are not optional extras layered onto physics. They are a direct consequence of how fields behave. Once the wave nature of electromagnetic fields was accepted, the universe appeared very different. Space was no longer a silent backdrop. It was alive with oscillations. Even in apparent darkness, fields could be moving, carrying energy beyond human senses. Most electromagnetic waves pass through you without notice. Radio waves from distant transmitters, microwaves from communication satellites, infrared radiation emitted by warm objects. They are present whether you pay attention or not. What determines whether a wave affects you strongly is not its existence, but its frequency and intensity, and how those properties interact with the structure of matter. That interaction would become crucial to understanding light itself. Because once electromagnetic waves were understood as a general phenomenon, it became impossible to treat visible light as something separate. Light was no longer special by decree. It was special only because of how our eyes evolved to respond to a narrow band of the electromagnetic spectrum. And with that realization, the story naturally shifts from waves in the abstract to the specific wave that dominates human experience, revealing how the invisible field oscillations that fill the universe give rise to colour, vision, warmth, and the familiar glow of the world around us. For most of human history, light occupied a strange position in our understanding of nature. It was familiar, essential, and yet fundamentally mysterious. People could describe how it behaved in simple terms. It travelled in straight lines, it reflected from mirrors, it bent when passing through glass or water, it cast shadows and revealed colour. But what light actually was remained unsettled for centuries. Was it a stream of particles, a vibration, something else entirely? The answer would only become clear once electromagnetic waves were understood not as an abstract mathematical outcome, but as a physical reality that filled space. Before that shift, light was often treated as its own category. Optics developed separately from electricity and magnetism. Laws of reflection and refraction were established without any reference to fields. Experiments with lenses and prisms advanced navigation, astronomy and vision science. Yet they did so without revealing light's deeper nature. Light worked, and that was often enough. One reason light resisted deeper explanation was that it behaves in ways that seem contradictory. It travels in straight lines, suggesting particle-like behaviour, but it also interferes with itself, producing patterns of bright and dark fringes that only waves can explain. These dual characteristics caused long-standing debate. Some favoured particle models, others favoured wave models. Both could explain some observations, but neither could explain all of them without strain. The turning point came when electromagnetic theory showed that waves could exist without a material medium. Once that barrier fell, light no longer needed a special explanation. It fit naturally into the field framework. According to Maxwell's equations, oscillating electric and magnetic fields propagate through space at a fixed speed. That speed matched the measured speed of light. This was not an approximate match or a coincidence within experimental error. It was exact within the limits of measurement available at the time. The implication was unavoidable. Light is an electromagnetic wave. This statement did not redefine light so much as relocate it. Light was no longer something separate that needed its own rules. It became one member of a much larger family of electromagnetic phenomena. What distinguished light from radio waves or X-rays was not its nature, but its frequency. Visible light occupies a narrow band of the electromagnetic spectrum. Its wavelengths are comparable to the size of molecules and atoms, which makes it particularly effective at interacting with matter in ways our eyes can detect. There is nothing inherently privileged about this band from the universe's point of view. It is privileged only from a biological one. Once light was understood as an electromagnetic wave, many of its familiar properties became easier to explain. Reflection occurs because the oscillating electric field of the wave pushes charges in a reflective surface. Those charges move in response, creating their own electromagnetic waves that cancel the original wave inside the material and reinforce it outward. The reflected wave is not light bouncing off a surface like a rubber ball. It is the result of fields interacting. Refraction, the bending of light as it enters a different medium, arises because electromagnetic waves travel at different effective speeds in different materials. The wave does not slow down because it is bumping into atoms like a crowd navigating obstacles. It slows because the oscillating field causes charges within atoms to shift slightly, re-radiating the wave with a small delay. The cumulative effect is a change in direction. Dispersion, the separation of light into colours by a prism, follows from the same principle. Different frequencies interact with matter slightly differently. Shorter wavelengths are delayed more than longer ones. As a result, white light spreads into a spectrum. Colour is not a property of light alone. It is a result of how electromagnetic waves interact with matter and with our sensory systems. Interference and diffraction, once puzzling, become natural consequences of overlapping fields. When two light waves pass through the same region of space, their electric and magnetic fields add together. Where they reinforce, brightness increases. Where they cancel, darkness appears. No particles need to collide. The pattern emerges from superposition. Understanding light as a wave also clarified why it carries energy and momentum. The energy is stored in the oscillating fields themselves. The momentum arises from the flow of energy through space. This explains why light can exert pressure, however small. Solar sails, for example, rely on this effect. Photons are often described as carrying momentum, but at the classical level, it is the field that does the work. One of the most important consequences of this view is that light does not require a medium. It does not need air, glass, or ether. It travels just as well through empty space. The space between stars is not a barrier. It is the environment through which electromagnetic fields naturally propagate. This explains how sunlight reaches Earth across millions of kilometers of near vacuum. The sun does not throw particles of light across space like stones. It accelerates charges in its hot plasma, generating electromagnetic waves that spread outward in all directions. Those waves arrive at Earth, interact with the atmosphere and surface, and deposit energy. Seeing light as an electromagnetic visitor rather than a local phenomenon reshapes perspective. Every beam of light you encounter began somewhere else. It is a messenger, carrying information about its source, encoded in its frequency, intensity, and polarization. Astronomers rely on this. By analyzing the electromagnetic radiation from distant objects, they infer composition, temperature, motion, and structure. Polarization, in particular, makes more sense in the field framework. Light waves have electric fields oscillating in specific directions. Filters can block or transmit light depending on this orientation. Polarization reveals information about scattering, reflection, and magnetic fields in distant regions of space. The electromagnetic nature of light also explains its interaction with electric charges at the atomic level. When light encounters an atom, its oscillating electric field can push electrons into new energy states. If the frequency matches the energy difference between states, the atom absorbs the light. If not, the light passes through or is scattered. This selective interaction is the basis of spectroscopy. Each atom and molecule has a characteristic set of frequencies it can absorb or emit. By studying these patterns, scientists identify substances across vast distances. The light from a distant star carries within it a detailed fingerprint of the elements present there. It also explains why some materials are transparent and others opaque. In transparent materials, the electromagnetic waves pass through with little energy loss. In opaque materials, the waves are absorbed, transferring energy to electrons and atoms, often producing heat. Once light is understood as electromagnetic, the boundaries between optics and electromagnetism dissolve. Mirrors, lenses, antennas, and waveguides all become variations on the same theme. They shape fields, they guide oscillations. They do not create special kinds of light. They manipulate existing electromagnetic waves. This unification had practical consequences as well. It allowed engineers to design devices using a single framework. Radio communication, radar, fiber optics, and wireless networks all rely on controlling electromagnetic waves. The same equations that describe sunlight also describe Wi-Fi. At the same time, the electromagnetic view of light exposed limitations in classical physics. Experiments involving very low light levels or very high frequencies revealed behaviours that could not be explained using waves alone. Light sometimes behaved as if it came in discrete packets of energy. This would later lead to quantum theory, but that development does not undo the field picture. It refines it. Even in quantum descriptions, electromagnetic fields remain central. Photons are not replacements for fields, they are quantized excitations of the electromagnetic field. The field is still there, underlying the behaviour. What matters here is that light is no longer an outsider. It is not a special exception. It is one of many ways electromagnetic fields move through space. It enters rooms, eyes, instruments and detectors not as a substance, but as a structured oscillation. This perspective also reframes everyday experience. When you turn on a lamp, you're not releasing light into the room as a thing. You're accelerating charges in a filament or semiconductor. Those accelerating charges disturb the electromagnetic field. The disturbance propagates outward. Some of it reaches your eyes. Your visual system responds to a narrow band of frequencies. The world becomes visible. When you step outside on a warm day, the heat you feel is largely infrared electromagnetic radiation interacting with your skin. When you feel the sun on your face, you are absorbing energy carried across space by fields that began oscillating long before they reached you. None of this requires intention or awareness on the part of the waves. They do not seek destinations. They propagate according to local rules. They fill space. They pass through most matter. They interact where conditions allow. Seeing light this way does not make it less remarkable. It makes it more connected. It ties vision, warmth, colour, and communication into a single framework. It shows that what we perceive as illumination is just one small window into a much larger electromagnetic environment. And once light is recognized as one visitor among many, it becomes natural to ask what else is passing through us unnoticed. Because visible light occupies only a tiny fraction of the electromagnetic spectrum. Above and below it lie vast ranges of waves we do not sense directly, yet which shape technology, climate, biology, and the structure of the modern world. Understanding light as an electromagnetic visitor does not close the story. It opens it outward, revealing that the space around us is constantly alive with signals, energies, and interactions beyond human perception, waiting to be explored by extending the same field-based thinking that first brought light into focus. Once light was understood as only one expression of electromagnetic activity, the boundaries of everyday perception began to feel strangely narrow. Visible light, the portion of the electromagnetic spectrum that human eyes respond to suddenly appeared not as the default, but as an exception, a thin slice carved out of something far larger. The world we see is shaped by this slice, but the world we live inside extends far beyond it. The electromagnetic spectrum is not a collection of separate phenomena stitched together by convention. It is a continuous range of waves, ordered by frequency or wavelength, with no natural breaks. The divisions we use, radio, microwave, infrared, visible, ultraviolet, X-ray, gamma, are practical labels, not fundamental categories. They reflect how waves are produced, detected, and interact with matter, not any change in underlying physics. At the low frequency end of the spectrum are radio waves. These waves have long wavelengths, sometimes stretching from meters to kilometers. Their oscillations are slow compared to visible light. Because of this, they interact gently with matter. They pass easily through air, clouds, walls, and even parts of the Earth's atmosphere. This makes them ideal for communication. Radio waves do not carry little radio-shaped objects. They are oscillations of electric and magnetic fields spreading outward from accelerating charges, typically inside antennas. By controlling the pattern of that acceleration, information can be encoded into the wave. Amplitude, frequency, and phase can all be varied to carry signals. The fact that radio waves can pass through buildings and travel long distances is not because they are powerful, but because their long wavelengths do not strongly disturb the structure of atoms. They nudge charges back and forth slowly enough that energy is not absorbed efficiently. The waves move on, leaving little trace. Microwaves occupy the region just above radio waves in frequency. Their wavelengths are shorter, comparable to the size of molecules. This makes their interaction with matter more selective. Water molecules, for example, respond strongly to microwave frequencies. They rotate and vibrate, converting electromagnetic energy into heat. This is the principle behind microwave ovens. The oven does not heat food by bombarding it with heat directly. It fills the space with electromagnetic waves tuned to frequencies that water molecules absorb readily. Those molecules begin to move more vigorously, and that motion spreads through the food as thermal energy. Microwaves are also central to communication. Satellite links, radar systems, and wireless networks rely on them. Their shorter wavelengths allow for higher data rates and more directional control than long radio waves, while still being able to travel through the atmosphere with relative ease. Above microwaves lies infrared radiation. Infrared waves are shorter still, and they are closely associated with heat. Any object with a temperature above absolute zero emits infrared radiation. The warmer the object, the higher the intensity and frequency of the emitted waves. Infrared radiation is how heat moves through empty space. When you stand near a fire, the warmth you feel on your skin is largely infrared, electromagnetic energy arriving from the flames. No air needs to carry it. The fields propagate directly from the source to you. Living organisms constantly emit infrared radiation. So do buildings, vehicles, and landscapes. Infrared cameras make this visible by translating radiation intensity into color or brightness. What appears as darkness to the eye becomes rich with structure in infrared. Visible light sits in a narrow window between infrared and ultraviolet. Its wavelengths are well matched to the energy scales of electronic transitions in atoms and molecules, particularly those involved in biological processes. This is not an accident. Eyes evolved to detect the part of the spectrum most readily available and most informative under sunlight. Sunlight itself peaks in the visible range because of the temperature of the sun's surface. Earth's atmosphere is also relatively transparent to visible light, allowing it to reach the ground. Together, these conditions made visible light a reliable carrier of information for early life. The colors we perceive correspond to different frequencies within this narrow band. Red light has longer wavelengths and lower frequencies. Blue light has shorter wavelengths and higher frequencies. There is no color outside this range because our eyes cannot respond to it, not because it does not exist. Just beyond visible light lies ultraviolet radiation. Ultraviolet waves have higher frequencies and carry more energy per oscillation. This increased energy allows them to interact more strongly with matter, particularly with electrons bound in atoms and molecules. Ultraviolet radiation can break chemical bonds. In small doses, this can be useful. It drives chemical reactions in the atmosphere and helps organisms produce vitamin D. In larger doses, it can damage DNA and proteins. This is why excessive exposure to ultraviolet light causes sunburn and increases cancer risk. Earth's atmosphere absorbs most ultraviolet radiation from the sun, particularly at the highest energies. This protective filtering is one of the reasons life can exist on land. Without it, the surface would be exposed to radiation capable of disrupting complex molecules. Above ultraviolet radiation are X-rays. X-rays have even shorter wavelengths and higher frequencies. Their energy is sufficient to penetrate many materials that visible light cannot. This penetrating power makes them valuable for imaging internal structures. X-ray imaging works because different tissues absorb X-rays to different degrees. Dense materials like bone absorb strongly. Soft tissues absorb less. The resulting contrast reveals internal anatomy without invasive procedures. The waves themselves pass through space and matter according to the same field rules as all electromagnetic radiation. At the highest frequency end of the spectrum are gamma rays. These waves carry enormous energy per oscillation. They are produced by the most energetic processes in the universe: nuclear reactions, particle interactions, and cosmic events such as supernova and black hole activity. Gamma rays interact intensely with matter. They can ionize atoms, disrupt molecular structures, and deposit energy deep inside materials. On Earth, they are relatively rare at ground level, but they are common in space. Instruments designed to detect them provide insight into extreme astrophysical environments. What unites all of these waves is not their source or effect, but their nature. They are all electromagnetic waves. They all consist of oscillating electric and magnetic fields. They all propagate at the same speed in a vacuum. They differ only in frequency, wavelength, and intensity. This continuity has profound implications. It means that the same underlying physics governs a radio broadcast, a thermal image, a sunbeam, and a cosmic gamma-ray burst. The differences we perceive arise from how matter responds to different frequencies, not from any fundamental change in the waves themselves. It also means that we're constantly immersed in electromagnetic activity beyond our senses. Radio waves from distant transmitters pass through our bodies. Infrared radiation from warm objects surrounds us. Cosmic radiation arrives from space. None of this feels dramatic because our nervous systems evolved to ignore most of it. Living inside this spectrum does not mean being passively bathed in random energy. It means existing in a structured environment where fields carry information, energy, and influence. Technology has learned to exploit this environment by shaping and detecting specific frequencies. Modern life depends on this shaping. Communication systems allocate different frequency bands to avoid interference. Medical imaging selects frequencies that interact predictably with tissue. Remote sensing relies on how surfaces reflect or emit radiation at different wavelengths. The spectrum also plays a role in climate. Earth absorbs sunlight mostly in the visible range and emits energy back into space as infrared radiation. Greenhouse gases selectively absorb infrared waves, trapping heat. This balance of absorption and emission is electromagnetic at its core. Biology, too, is tuned to the spectrum. Photosynthesis depends on specific wavelengths to drive chemical reactions. Circadian rhythms respond to light cues. Even animal navigation can involve sensitivity to electromagnetic fields and radiation beyond human perception. What is striking is how little of this requires conscious awareness. You do not need to sense radio waves for them to deliver information. You do not need to see infrared radiation for it to warm you. The fields operate regardless of perception. From a broader perspective, the electromagnetic spectrum reveals that the environment is layered. The visible world is just one layer, shaped by biological constraints. Beneath and beyond it lies a dense web of interactions unfolding continuously. This layered reality challenges intuition. It invites a shift away from thinking of the world as a collection of objects illuminated by light, toward thinking of it as a field-rich environment where illumination is just one kind of interaction among many. Once this shift occurs, it becomes easier to understand why electromagnetic fields matter so deeply. They are not just carriers of signals or sources of energy. They define how matter interacts across space. They determine which interactions are possible and which are suppressed. Living inside the spectrum means being shaped by invisible rules. It means that the space around you is active, structured, and responsive, even when it appears still. It means that the boundaries of experience are not the boundaries of reality. And as technology continues to expand the range of frequencies we generate and detect, the electromagnetic environment becomes increasingly shaped by human activity. Artificial signals overlay natural ones. The spectrum becomes crowded, managed, regulated. This raises questions not only about efficiency and interference, but about interaction with biological systems, with ecosystems, and with the planet as a whole. Those questions cannot be answered by treating electromagnetic waves as isolated tools. They require understanding the spectrum as an environment. Because the spectrum is not something we occasionally visit. It is something we inhabit continuously. Every moment unfolds within it, whether or not we are aware of its presence. Recognizing this does not make the world feel less solid. It makes it feel more layered, more connected, more intricate. The familiar surfaces of everyday life are still there, but they are embedded within a vast electromagnetic landscape that quietly supports, shapes, and transmits the processes that make modern existence possible. And once the spectrum is seen this way, as an invisible environment rather than a set of isolated technologies, attention naturally turns to how these fields operate not just around us, but through us, shaping the conditions of everyday life in ways that are subtle, measurable, and increasingly central to how the modern world functions. By the time electromagnetic fields are understood as something that fills space continuously, the boundary between physics and daily life becomes difficult to draw. These fields are not confined to laboratories, power stations, or antennas on distant hills. They operate quietly in the background of nearly every ordinary action, shaping outcomes so consistently that their presence becomes easy to overlook. The modern world functions not because electromagnetic fields are rare or powerful, but because they are stable, predictable, and everywhere. One of the most immediate ways electromagnetic fields appear in everyday life is through electricity delivered to homes and buildings. When you flip a light switch, nothing visible travels from the power plant to the bulb in that instant. Electrons in the wires do not rush from the source to the lamp at near light speed. Instead, an electric field already present in the wiring changes its configuration, and that change propagates through the circuit. The energy flows through the field surrounding the conductors, guided by their geometry, not carried by individual electrons racing along. This distinction matters because it reveals how deeply fields are involved even in the simplest electrical devices. The wires in a wall do not merely act as pipes for charge. They shape the electric and magnetic fields around them, directing energy from one place to another. The familiar hum of electrical infrastructure, the warmth of a heater, the glow of a lamp all emerge from how those fields are arranged and constrained. Electric motors offer another clear example. Inside a motor, electric currents create magnetic fields that interact with other magnetic fields. The result is motion. Nothing pushes directly against anything else in a mechanical sense. The fields exert forces, guiding conductors to rotate. Every fan blade turning, every washing machine spinning, every electric vehicle accelerating depends on this field-mediated interaction. Generators reverse the process. mechanical motion changes magnetic fields, inducing electric currents. Power stations exploit this symmetry on massive scales. Water turbines, steam turbines, and wind turbines all convert motion into electrical energy by reshaping electromagnetic fields. The fields do not care whether the motion comes from falling water, heated gas, or moving air. They respond to change in the same way every time. Even devices that appear purely electronic rely on fields rather than moving parts. Consider a smartphone. Signals move through it not as physical objects, but as variations in the electric potential and electromagnetic waves. Data stored in memory corresponds to arrangements of charge and field within microscopic structures. Touchscreens respond to changes in electric fields caused by your finger altering the local environment. Wireless communication makes the role of fields even more explicit. When a phone connects to a network, it does so by emitting and detecting electromagnetic waves. These waves pass through walls, air, and bodies with little resistance, guided only by the rules governing field propagation. There is no invisible wire connecting device to tower. The connection exists because both are embedded in the same electromagnetic environment. Navigation systems depend on the same principles. Global positioning relies on timing signals transmitted as electromagnetic waves from satellites. The accuracy of your location depends on how precisely those field oscillations are measured and compared. Even tiny delays matter. Without a detailed understanding of how electromagnetic waves propagate through space and time, such systems would be impossible. Household appliances quietly exploit electromagnetic fields in ways that are rarely noticed. Induction cooktops heat cookware not by direct contact with a flame or heating element, but by generating rapidly changing magnetic fields. Those fields induce currents in the metal of the pan, and the electrical resistance of the material converts that energy into heat. The cooktop itself remains relatively cool because the energy is deposited where the field interacts most strongly. Speakers and headphones transform electrical signals into sound through electromagnetic interaction. A changing electric current produces changing magnetic field, which exerts forces on a coil attached to a diaphragm. The diaphragm moves air, producing pressure waves we perceive as sound. The entire process depends on fields translating information between electrical and mechanical forms. Screens too rely on electromagnetic principles. Liquid crystal displays use electric fields to control the orientation of molecules that affect how light passes through them. Light-emitting diodes produce light when electric fields guide electrons into states where they release energy as electromagnetic radiation. Even the colors you see are shaped by how fields influence electrons within materials. Outside the home, electromagnetic fields continue their work unnoticed. Traffic signals, security systems, automatic doors, and sensors all depend on controlled field interactions. Credit cards and contactless payment systems use radio frequency fields to exchange information over short distances. The transaction completes not because something physical is handed over, but because fields briefly overlap in a specific way. Medical technology relies heavily on electromagnetic fields as well. Imaging techniques use carefully tuned fields to probe the interior of the body. Heart monitors detect tiny electrical signals produced by muscle cells. Brain activity is measured through electrical potentials that propagate through tissue and scalp. None of this would be possible if electromagnetic fields did not interact predictably with biological matter. Even cooking, cleaning, and climate control involve fields. Refrigerators move heat by using electric fields to drive compressors and fans. Air conditioners rely on motors and sensors shaped by electromagnetic interactions. Washing machines use fields to control motors, valves, and timing circuits. Lighting streets and cities depends on fields traveling long distances through transmission lines. Those lines are designed not just to carry current, but to manage electric and magnetic fields in ways that minimize loss and interference. The spacing of conductors, the materials used, and the voltages chosen all reflect an understanding of field behavior. Beyond technology, Electromagnetic fields shape natural processes we encounter daily. The Earth's magnetic field influences navigation systems, but it also affects how charged particles from the Sun interact with the atmosphere. Auroras appear when those particles are guided by magnetic field lines into the upper atmosphere, where they excite atoms and produce light. This is not a rare cosmic event. It is an ongoing interaction between fields and matter. Weather, too, involves electromagnetic effects. Lightning is an electrical discharge driven by large-scale electric fields built up within storm clouds. The crack of thunder is the sound of rapidly heated air expanding, but the event begins with field-induced charge separation over kilometers of sky. On a smaller scale, static electricity reminds us that electric fields can build up even in dry indoor environments. Walking across a carpet and touching a metal doorknob can result in a sudden discharge. The spark is brief, but it reveals how easily electric fields form and collapse around us. Biological systems operate in constant dialogue with electromagnetic fields. Nerve impulses are electrical signals guided by fields across cell membranes. Muscles contract in response to electric stimulation. The heart's rhythm is maintained by electrical waves moving through tissue. These are not analogies, they are literal field-driven processes. Vision itself depends on electromagnetic interaction. Photoreceptor cells respond to incoming electromagnetic waves by triggering electrical signals. Those signals propagate through neural networks, guided by electric fields at microscopic scales. What you perceive as sight is the result of layered electromagnetic processes, from the arrival of light to the firing of neurons. Even timekeeping relies on electromagnetic principles. Modern clocks use oscillations of electromagnetic fields to define seconds with extraordinary precision. Synchronization across networks depends on electromagnetic signals moving predictably through space. What is striking about all of this is how little effort is required to benefit from it. You do not need to understand electromagnetic fields to use a phone, turn on a light, or navigate a city. The fields do their work whether you are aware of them or not. Their reliability is what allows them to fade into the background. This invisibility can be misleading. It can create the impression that electromagnetic fields are artificial or optional, something added by technology. In reality, technology merely reshapes fields that already exist. It organizes them, focuses them, modulates them. The underlying environment remains the same. The distinction between natural and artificial fields is therefore less clear than it seems. A radio transmitter generates waves, but so does the sun. A power line produces a magnetic field, but so does the Earth. The difference lies in scale, frequency, and control, not in fundamental nature. Everyday life unfolds within this field-rich environment. The walls around you do not block fields entirely. The air does not carry them as a medium. They pass through, around, and between objects according to consistent rules. Recognizing this does not require seeing the world as fragile or dangerous. Electromagnetic fields have always been part of the environment. Life evolved within them. What has changed is how densely and deliberately we now generate certain frequencies. This density brings benefits, convenience, connectivity. It also invites questions. How do these fields interact with living systems over long periods? How do multiple sources overlap? How should environments be designed to manage exposure responsibly? Those questions do not arise from fear. They arise from awareness, from understanding that fields are not abstract background features, but active participants in everyday processes. Once this perspective takes hold, everyday life looks subtly different. Devices are no longer boxes that magically work. They are arrangements of matter designed to shape fields in precise ways. Infrastructure becomes a vast, coordinated manipulation of invisible structure. And because these fields are continuous, because they extend beyond individual devices and buildings, their influence does not stop at the edge of a gadget or a wall. It spreads outward, interacting with larger systems, including the planet itself. That realization naturally leads beyond homes and cities toward the larger field environment surrounding Earth as a whole, where electromagnetic interactions operate not just locally but globally, shaping conditions that have existed long before modern technology and that continue to play a protective role on a planetary scale. Long before humans learned to generate electromagnetic fields deliberately, long before power grids, radios, or satellites, Earth itself was already surrounded by a vast and active electromagnetic structure. This structure does not announce itself loudly. It does not glow in daylight or make noise as it works, and yet, without it, life on the surface of the planet would look very different, if it could exist at all. The planetary environment is not just shaped by rock, water, and air, but by fields extending far beyond the atmosphere, quietly interacting with space. At the centre of this structure is Earth's magnetic field. To a compass needle it appears simple. North points north. But that simplicity hides a system that stretches tens of thousands of kilometres into space, forming a protective envelope around the planet. This magnetic field is not static, and it is not a leftover artifact from Earth's formation. It is generated continuously by motion deep inside the planet. Beneath the crust and mantle lies Earth's outer core, a vast region of molten iron and nickel. This liquid metal is in constant motion, driven by heat escaping from the planet's interior and by Earth's rotation. As electrically conductive material moves through an existing magnetic field, it generates electric currents. Those currents, in turn, generate magnetic fields. The process reinforces itself. This self-sustaining mechanism is known as the geodynamo. The result is a magnetic field that emerges from the planet near one geographic pole, arcs through space, and re-enters near the other. But this picture, often drawn simply in textbooks, is only a rough approximation. In reality, the field is complex, dynamic, and uneven. Its strength varies from place to place. Its orientation drifts over time. Its structure responds constantly to both internal and external influences. The field does not stop at the atmosphere. It extends outward into space, forming a region called the magnetosphere. This region is shaped not only by Earth's internal field, but by its interaction with the solar wind, a continuous stream of charged particles flowing outward from the sun. These particles carry their own magnetic fields, and when they encounter Earth's magnetosphere, the interaction becomes a negotiation between two field systems. On the side of Earth facing the sun, the magnetosphere is compressed. On the opposite side, it stretches into a long tail that extends far beyond the Moon's orbit. This structure is not rigid. It flexes, ripples, and reshapes itself in response to solar activity. During periods of intense solar storms, the magnetosphere can be disturbed dramatically. What makes this field environment so important is its role as a shield. Charged particles from the sun and from more distant cosmic sources are deflected by magnetic fields. Instead of striking the atmosphere directly, many of them are guided around the planet. Without this deflection, Earth's atmosphere would be gradually stripped away by the constant bombardment of energetic particles, as appears to have happened on Mars. The magnetic field does not block all incoming particles. Some are funneled along field lines toward the polar regions, where they collide with atoms high in the atmosphere. These collisions excite the atoms, causing them to emit light. This is the origin of auroras. The shimmering curtains of green, red, and purple light near the poles are visible evidence of electromagnetic interactions on a planetary scale. Auroras are not rare accidents. They are a direct manifestation of Earth's field interacting with space weather. When solar activity increases, auroras intensify and expand toward lower latitudes. When the sun is quieter, they retreat toward the poles. The light show is the surface expression of an invisible process playing out far above. Beyond their visual beauty, auroras reveal something deeper. They show that Earth is not isolated from space. It is immersed in a flow of energy and particles, and its electromagnetic field mediates that interaction. The planet is constantly exchanging energy with its environment, guided by field lines that reach far beyond the surface. The atmosphere itself participates in electromagnetic processes. Thunderstorms generate large-scale electric fields between clouds and the ground. These fields can span kilometers and store enormous amounts of energy. When the electric field becomes strong enough, it breaks down the insulating properties of air, resulting in lightning. Lightning is not merely a dramatic discharge. It is a rapid reconfiguration of electric fields. Charges separate within storm clouds due to collisions between ice particles and water droplets. The resulting field grows until it can no longer be sustained. The discharge equalizes the field, releasing energy as light, heat, and sound. Even in fair weather, Earth's atmosphere maintains a global electric circuit. The surface of the planet carries a net negative charge relative to the upper atmosphere. Thunderstorms act as generators, maintaining this separation by pumping charge upward. In regions far from storms, a weak but measurable electric field exists between ground and sky. This field is small but persistent. This global electric environment influences atmospheric chemistry, cloud formation, and possibly even climate processes. While many details remain under investigation, it is clear that Earth's electromagnetic environment is not a passive backdrop. It participates actively in the planet's behavior. Beyond the atmosphere, the interaction between Earth's magnetic field and the solar wind creates complex dynamics. When the solar wind is calm, the magnetosphere remains relatively stable. When the sun releases bursts of energetic particles during solar flares or coronal mass ejections, the magnetosphere absorbs and redirects that energy. Sometimes the energy input is large enough to induce electric currents in Earth's upper atmosphere and even at the surface. These geomagnetically induced currents can flow through power grids, pipelines, and communication cables. In extreme cases, they can disrupt electrical infrastructure, damage transformers, and interfere with navigation systems. Such events are rare, but they highlight the fact that human technology is now coupled to planetary-scale electromagnetic processes. Power lines are not isolated wires. They are embedded in Earth's field environment. Changes in that environment can have direct consequences. Satellites orbiting Earth operate within the magnetosphere. They are exposed to varying levels of radiation depending on their orbit and solar conditions. Satellite design must account for this. Shielding, redundancy, and operational protocols are shaped by an understanding of space electromagnetic environments. Navigation systems rely on electromagnetic signals passing through the ionosphere, a region of the upper atmosphere where solar radiation ionizes gases, creating a plasma. This plasma interacts strongly with electromagnetic waves, bending, delaying, and sometimes disrupting signals. Radio communication, GPS accuracy, and radar performance all depend on ionospheric conditions. The ionosphere itself is structured by Earth's magnetic field. Charged particles spiral along field lines, creating layers and irregularities that change with time of day, season, and solar activity. This dynamic environment is both a resource and a challenge for communication technologies. From a biological perspective, Earth's electromagnetic environment has been part of the background conditions for life from the beginning. Organisms evolved under the influence of the planet's magnetic field and ambient electromagnetic radiation. Some species appear to have developed sensitivity to these fields. Migratory birds, sea turtles, and certain insects are believed to use Earth's magnetic field as part of their navigation system. The exact mechanisms are still being studied, but evidence suggests that biological systems can detect and respond to subtle magnetic cues. This sensitivity is not mystical. It arises from interactions between fields and molecules within cells. Even human biology operates within this field environment. The magnetic field influences how charged particles move in the upper atmosphere, which in turn affects radiation levels at the surface. While the field is too weak to directly influence most physiological processes, it contributes to the broader environmental conditions that shape life. The planetary shield is not permanent in its current form. Geological records show that Earth's magnetic field has reversed polarity many times over its history. During these reversals, the field weakens and becomes more complex before re-establishing itself in the opposite orientation. These transitions can last thousands of years. There is no evidence that past reversals caused mass extinctions, but they likely altered radiation exposure and atmospheric processes. Life persisted, adapted, and continued. This resilience suggests that the electromagnetic environment, while important, is one factor among many shaping planetary habitability. What makes Earth's electromagnetic shield especially significant is how it connects the planet to the larger cosmos. Earth is not sealed off from space. It is engaged in constant interaction, moderated by fields that extend beyond the visible atmosphere. The boundary between Earth and space is not a wall, but a dynamic interface. This perspective changes how the planet is seen. Earth is not just a rock orbiting the Sun. It is a field-generating body embedded in a larger electromagnetic system. Its internal motions create a magnetic structure that reaches into space. That structure, in turn, shapes how energy and matter from the Sun interact with the planet. Understanding this system has practical importance. Space weather forecasting aims to predict solar events that could disrupt satellites, power grids, and communication networks. These predictions depend on models of electromagnetic interactions between the Sun and Earth. As human activity extends further into space, the relevance of Earth's electromagnetic environment will only grow. Missions to the Moon, Mars, and beyond must contend with different field conditions. The absence of a strong planetary magnetic field on Mars, for example, exposes the surface to higher radiation levels, shaping considerations for exploration and habitation. At the same time, studying Earth's field provides insight into other planets. By comparing magnetic environments, scientists learn about planetary interiors, atmospheres, and evolutionary histories. The presence or absence of a magnetic field reveals clues about a planet's past and future. What emerges from all of this is a sense that electromagnetic fields operate on scales far beyond human intuition. They are not limited to wires and devices. They extend outward, shaping planetary environments and mediating interactions between worlds. And yet, despite their vast reach, these fields are governed by the same principles that operate inside a smartphone or a power cable. The rules do not change with scale, only the context does. This continuity is what makes the planetary electromagnetic shield such a powerful example of invisible forces shaping reality. The same field concepts that explain a compass needle also explain auroras. The same interactions that drive a motor also deflect solar particles. Recognizing this does not diminish the wonder of the planet. It deepens it. It reveals Earth not as an isolated object, but as an active participant in a field-filled universe. And once the planetary scale is understood, once it becomes clear that electromagnetic fields shape not only technology and daily life, but the very conditions of life on Earth, the next question arises naturally. How do these same fields interact with living systems directly, not just as background conditions, but as influences that operate within cells, tissues, and organisms themselves, shaping biology in ways that are subtle, complex, and still being explored? Living organisms do not exist apart from electromagnetic fields. They have never done so. From the earliest stages of life on Earth, biology has unfolded within an environment shaped by electric and magnetic influences, from the planetary scale down to the interior of individual cells. These fields are not external pressures imposed on life at a late stage. They are woven into the conditions under which life emerged, adapted, and diversified. At the most basic level, life is electrical. This statement is not metaphorical. Every living cell maintains electrical differences across its membrane. These differences arise because ions, charged atoms like sodium, potassium, calcium, and chloride, are distributed unevenly between the inside and outside of the cell. Maintaining that imbalance requires energy, and the result is an electric potential. Without it, the cell cannot function. This membrane potential is not a minor detail. It governs how substances enter and leave the cell. It determines how cells communicate. It influences how proteins fold and how biochemical reactions proceed. The interior of a cell is not a neutral chemical soup. It is an electrically structured environment. In nerve cells, this electrical structure becomes especially prominent. Neurons communicate using rapid changes in membrane potential, known as action potentials. When a neuron fires, voltage-gated ion channels open and close in a precise sequence, allowing charged particles to move across the membrane. This movement creates a wave of electrical change that travels along the cell. What moves is not a particle sliding down a wire, but a disturbance in an electric field propagating along a biological structure. The speed, direction, and timing of this propagation are governed by the same electromagnetic principles that apply to any conductive system, shaped here by the geometry and material properties of living tissue. Muscle cells operate on similar principles. Electrical signals trigger contractions by releasing calcium ions that allow molecular motors to engage. The coordination of movement, from the beating of the heart to the motion of limbs, depends on carefully timed electrical activity. A disruption in these signals can have immediate and serious consequences. The heart itself functions as a rhythmic electrical system. Specialized cells generate spontaneous electrical impulses that spread through cardiac tissue in a coordinated pattern. This pattern ensures that chambers contract in the correct sequence. Medical devices that monitor heart activity do so by detecting electric fields at the skin surface, fields generated by the collective behavior of billions of cells. The brain, often described in chemical terms, is fundamentally electromagnetic as well. While neurotransmitters play an essential role in communication between neurons, the signals that travel within neurons and across neural networks are electrical. Brain activity can be measured by detecting patterns of electric potential and magnetic fields outside the skull. These measurements are not indirect guesses. They are direct detections of electromagnetic activity generated by living tissue. Electroencephalography and magnetoencephalography rely on this principle. They work because biological processes produce measurable fields. At smaller scales, electromagnetic interactions shape the behavior of molecules that make life possible. Chemical bonds themselves are electromagnetic in origin. Atoms bind together because of interactions between electric charges and fields. The structure of proteins, the pairing of DNA bases, and the folding of complex molecules are all governed by electromagnetic forces. Even the recognition between molecules, such as an enzyme binding to its substrate, depends on electric charge distributions and field interactions. Molecules are not featureless objects colliding randomly. They carry patterns of charge that guide how they interact. These patterns determine specificity and efficiency in biological reactions. Water, the medium of life, also plays a critical role in electromagnetic interactions. Water molecules are polar, meaning they have an uneven distribution of charge. This allows them to respond to electric fields and to shield charges within biological systems. The behavior of ions in solution, the stability of proteins, and the structure of cell membranes all depend on this property. Because biology relies so heavily on electromagnetic interactions at small scales, it is natural to ask how larger-scale fields influence living systems. This question has been approached carefully and at times controversially. The answer is not simple, and it does not lend itself to dramatic conclusions. Earth's magnetic field, for example, is weak compared to the fields inside cells or near electronic devices. It does not directly drive biological processes in most organisms, However, evidence suggests that some species are sensitive to it. Migratory birds, sea turtles, and certain fish appear to use magnetic cues as part of their navigation strategy. The mechanisms behind this sensitivity are still being studied. Some hypotheses involve magnetite, a magnetic mineral found in small quantities in certain tissues. Others involve quantum effects in molecules whose behavior is influenced by magnetic fields. What matters here is not the details, but the principle. Biological systems can, under specific conditions, detect and respond to weak fields. Plants too respond to electromagnetic conditions. Light, as an electromagnetic wave, drives photosynthesis. Different wavelengths trigger different developmental responses. Plants adjust growth patterns based on light quality, intensity, and duration. These responses are mediated by molecules that absorb electromagnetic radiation and initiate biochemical changes. Circadian rhythms in many organisms are regulated by light exposure. The timing of sleep, feeding, hormone release, and cellular repair cycles depends on electromagnetic signals from the environment. Artificial lighting can disrupt these rhythms, demonstrating how sensitive biological systems are to changes in electromagnetic exposure. At the cellular level, electric fields play a role in development and healing. During embryonic development, spatial patterns of electric potential guide cell differentiation and tissue formation. Cells respond not only to chemical gradients, but also to electrical ones. These bioelectric cues help establish structure long before organs are fully formed. Wound healing also involves electric fields. When tissue is damaged, ionic imbalances create local electric fields that guide cell migration toward the wound site. This process has been observed across many species. The fields do not heal the tissue directly, but they provide directional information that coordinates repair. These examples show that biology does not merely tolerate electromagnetic fields, it uses them. It integrates them into control systems that operate alongside chemical signaling. This integration is subtle and context-dependent. Fields do not override biology, they participate in it. Given this deep integration, it is reasonable to ask how modern electromagnetic environments interact with living systems. Human activity has introduced new sources of electromagnetic fields at frequencies and intensities that did not exist naturally at large scales. Power lines, communication systems, and electronic devices all contribute to this environment. Research into biological effects of these fields has been extensive. The consensus that has emerged is nuanced. At sufficiently high intensities, electromagnetic fields can cause heating or tissue damage. This is well understood and forms the basis for safety standards. At lower intensities, typical of everyday exposures, effects are harder to detect and often inconsistent. This does not mean that low-level fields have no interaction with biology. It means that biological systems are complex, adaptive, and influenced by many variables. Isolating subtle effects requires careful study. Results must be reproducible and biologically meaningful, not merely statistically suggestive. One important distinction is between ionizing and non-ionizing radiation. High-frequency electromagnetic radiation, such as X-rays and gamma rays, carries enough energy to break chemical bonds and damage DNA directly. This type of radiation poses clear risks and is tightly regulated. Lower frequency radiation, such as radio waves and microwaves used in communication, does not carry enough energy per oscillation to cause direct chemical damage. Its primary interaction with tissue is through heating at sufficiently high power levels. At everyday exposure levels, heating effects are negligible. Understanding this distinction helps separate genuine biological mechanisms from misconceptions. Electromagnetic fields do not imprint intentions or disrupt biology in vague ways. Their interactions follow physical rules. When effects occur, they do so through specific measurable pathways. At the same time, biology's sensitivity to timing, pattern, and context means that not all interactions are obvious. A field that is harmless in one configuration may have effects in another if it aligns with biological rhythms or structures. This is why research continues, refining exposure guidelines and improving understanding. What is clear is that living systems are not passive objects immersed in fields. They are active, responsive systems that generate their own fields and interact with external ones. The electromagnetic environment is not an external stressor alone. It is part of the medium in which life operates. This perspective reframes questions about safety and exposure. Rather than asking whether fields are present, the relevant questions concern strength, frequency, duration, and pattern. It is not presence that matters, but interaction. From an evolutionary standpoint, life has always existed in a field-rich environment. The sun's radiation, Earth's magnetic field, and atmospheric electricity have been constants. Organisms adapted within these conditions, incorporating electromagnetic interactions into their physiology. Modern technology adds layers to this environment, but it does not introduce an entirely new category of influence. It reshapes an existing one. Understanding how biology responds requires both physical insight and biological context. As research progresses, electromagnetic tools are increasingly used deliberately in medicine. Electrical stimulation is used to treat neurological disorders. Magnetic fields are used to image internal structures and guide therapies. These applications work because biology responds predictably to controlled fields. This deliberate use highlights an important point. Fields are not inherently beneficial or harmful. They are tools and conditions. Their effects depend on how they are applied and how systems respond. Seen this way, biology in a sea of fields is not a story of vulnerability alone. It is a story of integration. Life has learned to operate within electromagnetic environments, to exploit them, to generate its own, and to remain stable amid constant fluctuations. The same principles that allow neurons to fire and hearts to beat also allow organisms to function in environments filled with natural and artificial electromagnetic activity. This continuity is not accidental. It reflects the fact that life and physics are not separate domains. They are expressions of the same underlying rules. As understanding deepens, the challenge is not to fear the invisible, but to describe it accurately, to distinguish mechanisms from speculation, to recognize where effects are real, where they are negligible, and where knowledge is still incomplete. Because electromagnetic fields are not going away. They are fundamental to how the universe operates and to how modern society functions. Living systems will continue to exist within them, adapt to them, and increasingly use them in intentional ways. And as biology and technology become more intertwined, the need to measure, quantify, and understand these invisible interactions grows. Which brings attention naturally to the question of how fields are detected in the first place, how something invisible is made measurable, and how confidence is built around phenomena that cannot be seen, but only inferred through careful observation and instrumentation. Understanding electromagnetic fields would not have progressed very far if they had remained forever invisible and intangible. The moment scientists accepted that fields were real, the next challenge became unavoidable. If something cannot be seen directly, how do you know it is there at all? And more importantly, how do you measure it in a way that allows prediction, comparison, and control? The history of electromagnetism is inseparable from the history of instruments. Fields themselves do not leave marks on paper or announce their presence with sound. They reveal themselves only through how they influence matter. Measuring the unseen therefore became an exercise in carefully designed interactions, using objects whose behaviour under electromagnetic influence could be trusted and interpreted. The earliest measurements were indirect and qualitative. A compass needle turning was not a number. It was an indication. Iron filings arranging themselves into patterns did not provide a scale or unit, but they did provide structure. These early tools were not measuring strength in any strict sense, but they were revealing geometry, direction, and relative intensity. As science matured, the need for precision grew. It was no longer enough to say that one magnet was stronger than another, or that a current caused a deflection. Researchers needed ways to quantify how strong a field was at a specific location, how it varied with distance, and how it changed over time. Electric charge was one of the first electromagnetic quantities to be measured with some consistency. Early devices such as electroscopes detected the presence of charge by observing the separation of thin metal leaves. The greater the charge, the greater the separation. This was still indirect, but it allowed comparison. One charge could now be said to be larger than another in a reproducible way. From there, attention turned to force. If a charged object exerted a force on another charged object, that force could be measured mechanically. Springs, balances, and torsion devices converted invisible influence into visible motion. By measuring how much a known object moved under electromagnetic influence, scientists could infer field strength. This approach marked a crucial conceptual step. Fields themselves were still not being measured directly. What was being measured was the response of matter placed within the field. The assumption, which proved reliable, was that the response followed consistent rules. If those rules were known, the field could be inferred. Magnetic fields posed similar challenges. Early measurements relied on the behavior of compass needles and magnetic dipoles. The angle of deflection provided information about the local field direction. The force required to twist a magnet away from alignment provided information about strength. Over time, these methods became more refined. Instruments were calibrated, units were standardized. What had once been a qualitative observation became a quantitative science. Magnetic field strength could be expressed as a number, comparable across experiments and locations. One of the most important developments in measuring fields was the realization that time mattered. Fields are not always static, they can change, oscillate, and propagate. Measuring a field at a single moment is not enough if the field is dynamic. To capture changing fields, scientists needed instruments that could respond quickly and faithfully. Coils of wire became essential tools. A changing magnetic field induces an electric current in a coil. By measuring that current, information about how the field was changing could be obtained. This principle allowed time-varying fields to be studied in detail. Oscilloscopes, for example, display electrical signals as functions of time. They translate invisible variations in electric potential into visible traces. What appears on the screen is not the field itself, but the effect of the field on a controlled electronic system. As electromagnetic waves entered the picture, measurement became even more subtle. Waves propagate through space, carrying energy and information. Measuring them requires capturing oscillations that may occur millions or billions of times per second. Antennas became the bridge between fields and instruments. An antenna does not collect waves like a net catches fish. It interacts with the electromagnetic field, allowing the field to induce currents that can be amplified and analyzed. The shape, size, and orientation of the antenna determine which frequencies it responds to most strongly. This selectivity is essential. It allows specific portions of the electromagnetic spectrum to be isolated and studied. Radio telescopes, for example, use large antennas to detect faint signals from space. These signals may have traveled for millions of years before interacting with the detector. At higher frequencies, different techniques are required. Infrared radiation is measured using sensors that respond to tiny temperature changes caused by absorbed energy. Visible light is measured using photodetectors that convert incoming electromagnetic waves into electrical signals. Ultraviolet and X-ray radiation require materials that can absorb high-energy photons and release measurable charge in response. Across all of these methods, the underlying strategy is the same. Let the field interact with matter in a controlled way. Measure the matter's response. Infer the properties of the field. This strategy has a powerful implication. Fields are not measured in isolation. They're always measured through interaction. There is no instrument that reads out field strength without itself becoming part of the field environment. Measurement is participation. This does not make measurement unreliable, it makes it contextual. Instruments are designed to interact in known ways. Their behaviour under electromagnetic influence is predictable and repeatable. Calibration ensures that one measurement can be compared to another. Units play a critical role here. Electric field strength, magnetic field strength, frequency, wavelength, and power are all expressed in standardized units. These units allow measurements made in different laboratories, at different times, and with different instruments to be meaningfully compared. The development of precise measurement also revealed something unexpected. Fields can be extraordinarily weak and still be detected. Modern instruments can measure magnetic fields far weaker than Earth's field and electric signals far smaller than those produced by a single neuron. This sensitivity has expanded what can be studied. Brain activity, heart rhythms, atmospheric electricity, and cosmic radiation all produce signals that can now be detected and analysed. What was once invisible in principle is now invisible only to unaided senses. Measurement also allows fields to be mapped. Rather than recording a single value, instruments can be moved through space, building up a picture of how field strength and direction vary. This spatial information is essential for understanding structure. Mapping reveals that fields are rarely uniform. They have gradients, boundaries, and regions of complexity. Power lines produce distinct field patterns. Devices create localized concentrations. Planetary fields vary with latitude and altitude. These patterns matter. In engineering, measurement guides design. Circuits are shaped to control field distribution. Shielding is added where fields might interfere. Frequencies are chosen to minimize unwanted interactions. None of this is guesswork. It is grounded in measurement. In medicine, measurement allows diagnosis and monitoring. Electrical signals from the heart and brain are recorded to assess health. Imaging techniques rely on measured interactions between fields and tissue. Treatment decisions are based on quantitative data, not impressions. In environmental science, electromagnetic measurements monitor lightning activity, solar storms, and space weather. These measurements inform predictions that protect infrastructure and technology. Again, invisible processes become manageable through careful observation. There is also an important philosophical shift embedded in all of this. Measuring the unseen forces redefinition of what counts as real. Reality is no longer limited to what can be seen or touched directly. It includes what can be inferred reliably through interaction. Electromagnetic fields are real not because they appear as objects, but because they produce consistent, measurable effects. Their reality is operational. They do work. They transfer energy. They obey laws. Measurement makes this reality accessible. At the same time, measurement introduces limits. No instrument is perfect. Every measurement has uncertainty. Recognizing this is part of scientific maturity. Confidence does not come from eliminating uncertainty, but from understanding and bounding it. As measurement techniques improve, they often reveal new layers of complexity. Finer resolution uncovers fluctuations. Greater sensitivity reveals background noise. Each advance answers questions and raises new ones. This process never truly ends. Measuring electromagnetic fields is not about reaching a final, complete description. It is about refining understanding, expanding capability, and reducing ambiguity. What emerges from this long effort is a world that is no longer defined solely by what can be seen. It is defined by what can be detected, quantified, and modelled. Invisible fields become part of the working landscape of science and technology. And once fields can be measured reliably, once their strengths, frequencies, and patterns can be quantified, it becomes possible to ask more practical and more sensitive questions. Not just what fields exist, but how strong they are in everyday environments, how they vary over time, and what levels of exposure matter. Those questions move the discussion from description into assessment, from understanding fields as neutral features of reality into considering how they interact with human systems over long periods, which naturally leads to the topic that often sits quietly beneath public curiosity and concern: health, safety, and the risks that are sometimes misunderstood when invisible forces become part of daily life. By the time electromagnetic fields became measurable, predictable, and mathematically describable, they stopped being merely objects of study and became tools. Modern technology is, in many ways, the art of shaping electromagnetic fields with precision. Not forcing them, not fighting them, but arranging materials and motion so that fields behave in ways that serve specific purposes. Once this perspective settles in, much of the technological world begins to look less like a collection of machines and more like a landscape of carefully guided invisible structure. At the heart of most modern technology is the controlled movement of electric charge. Charges in motion create fields. Fields changing in time move energy. That simple chain underlies everything from the smallest electronic sensor to the largest power grid. What differs is scale, frequency, and the degree of control. Consider the simplest electronic circuit. A power source establishes an electric potential difference. Conductive paths guide charge movement. Components such as resistors, capacitors, and inductors do not merely block or allow current. They shape electric and magnetic fields locally. A resistor dissipates energy by allowing fields to interact with the atomic structure of a material, converting organized energy into heat. A capacitor stores energy by maintaining an electric field between conductive surfaces. An inductor stores energy in a magnetic field generated by current flow. None of these components work because electrons move particularly fast. They work because fields rearrange themselves in predictable ways. In alternating current systems, for example, energy flows back and forth without net transport of charge over long distances. What oscillates is the field configuration, not the particles themselves. Scaling this up leads directly to power generation and distribution. Electrical grids operate by maintaining oscillating electric and magnetic fields across vast networks of conductors. The familiar hum of high-voltage transmission lines is a byproduct of these fields interacting with air and materials. Transformers rely on magnetic fields changing in time to transfer energy between circuits without physical contact, allowing voltages to be stepped up or down efficiently. Without this ability to shape fields, long-distance power transmission would be impractical. High voltages reduce energy loss by shaping electric fields to move energy with minimal current. Grid stability depends on synchronizing field oscillations across entire regions. Blackouts often occur not because wires fail, but because field relationships fall out of alignment. At smaller scales, electronics compress these same principles into microscopic spaces. In a computer processor, billions of transistors switch electric fields on and off at extraordinary speeds. Each switch represents a local reconfiguration of an electric field that either allows or prevents charge movement. The computation itself is a choreography of field changes. Data storage relies on electromagnetic effects as well. In magnetic storage devices, information is encoded in the orientation of magnetic domains. These domains are regions where atomic-scale magnetic moments align. Writing data means reshaping magnetic fields to flip those orientations. Reading data means detecting the resulting field patterns. Even in solid-state memory, where magnetism plays a smaller role, electric fields determine how charges are trapped and released within materials. Bits are not abstract symbols. They are physical states maintained by field configurations that must remain stable over time. Communication technologies extend this field control outward into space. Radio transmitters, cellular towers, and satellites all operate by accelerating charges in controlled patterns. That acceleration generates electromagnetic waves that propagate away from the source. Modulation techniques encode information by varying amplitude, frequency, or phase of these waves. The environment through which these waves travel is not empty in the practical sense. Buildings, terrain, atmosphere, and even weather influence how fields propagate. Engineers design systems with this in mind, choosing frequencies and power levels that balance range, penetration, and interference. Optical communication takes these ideas into the visible and near-visible spectrum. Fiber optic cables guide electromagnetic waves by confining them within materials whose refractive properties shape the field. Light does not bounce like a ball inside a fiber. It remains trapped because the field configuration cannot escape given the boundary conditions. This ability to guide light allows enormous amounts of information to be transmitted with minimal loss. Global communication infrastructure depends on this. Undersea cables carrying data between continents rely on stable electromagnetic wave propagation across thousands of kilometers. Sensing technologies also depend heavily on electromagnetic fields. Radar systems emit radio waves and detect reflections to determine distance, speed, and shape of objects. LIDAR uses higher frequency light waves to map environments with precision. These systems work because fields interact with matter in consistent ways that can be measured and interpreted. Medical imaging technologies provide some of the most striking examples of field-based technology. Magnetic resonance imaging uses strong magnetic fields and carefully timed electromagnetic pulses to probe the behavior of atomic nuclei in the body. The resulting signals reveal detailed internal structures without surgical intrusion. Other imaging methods rely on electromagnetic absorption and scattering. X-ray imaging, for example, exploits how high-frequency electromagnetic waves interact differently with various tissues. Each technique is a specific application of field-matter interaction. Even technologies not usually associated with electromagnetism depend on it deeply. Modern transportation systems rely on electromagnetic sensors for navigation, control, and safety. Aircraft instruments detect fields for communication and positioning. Trains use electromagnetic signaling and, in some cases, magnetic levitation to reduce friction. Energy technologies increasingly exploit electromagnetic principles in new ways. Solar panels convert electromagnetic radiation into electric fields that drive charge separation. Wind turbines convert mechanical motion into changing magnetic fields that induce current. Battery technology depends on controlling electric potentials at chemical interfaces. Lighting has undergone a similar transformation. Incandescent bulbs relied on heating materials until they emitted light. Modern lighting technologies shape electromagnetic emission more efficiently, producing specific frequencies with minimal waste. The result is less energy lost as unwanted radiation. Even seemingly mechanical devices often rely on electromagnetic control. Cameras use electric fields to manipulate image sensors. Printers use fields to place ink or toner precisely. Industrial machinery relies on electromagnetic actuators and feedback systems to achieve accuracy and repeatability. What unites all of these applications is not complexity for its own sake, but predictability. Electromagnetic fields obey consistent rules across scales. Once those rules are understood, they can be exploited repeatedly. Technology becomes reliable because the fields are reliable. This reliability has also allowed fields to fade from awareness. People do not think about electromagnetic wave propagation when making a phone call or switching on a light. The technology works precisely because the underlying field behavior is stable and well managed. At the same time, this invisibility can create a sense of abstraction. Devices appear to function through software or logic alone. The physical reality of fields shaping energy and information can be forgotten. Yet when systems fail, often due to interference, noise, or unexpected coupling, the field nature becomes suddenly obvious again. Electromagnetic compatibility is a major concern in modern design. Devices must operate without interfering with one another. This requires managing unintended field emissions and susceptibilities. Shielding, grounding, and filtering are not afterthoughts. They are essential elements of field control. As technology becomes denser and more interconnected, managing the electromagnetic environment becomes increasingly important. Urban areas are saturated with overlapping fields from countless sources. systems must be designed to coexist without conflict. This coexistence extends beyond devices to infrastructure and ecosystems. Power lines, communication towers, and transportation networks shape large-scale field patterns. Understanding those patterns helps minimize energy loss, reduce interference, and ensure safety. Technology also increasingly pushes into regimes that test existing understanding. Higher frequencies, faster switching speeds, and stronger fields reveal effects that were negligible at lower scales. At these edges, careful measurement and modelling are required to avoid unintended consequences. What remains consistent through all of this is the central role of electromagnetic fields as mediators. They move energy without mass. They transmit information without contact. They allow systems to interact across space. Modern technology does not create these capabilities from nothing. It aligns itself with the underlying structure of the universe. It works because the universe already supports field-based interaction. Seen this way, technological progress is not about overpowering nature. It is about learning how to cooperate with it. Devices succeed when they respect the rules governing fields. Failures often occur when those rules are ignored or oversimplified. This perspective also clarifies why technological limits often appear where they do. Maximum data rates, signal delays, energy efficiency constraints, and interference thresholds are not arbitrary. They arise from fundamental field behavior. As reliance on electromagnetic technology grows, so does the importance of understanding not just how to use fields, but how they interact with environments and living systems over time. The same properties that make fields useful, invisibility, persistence, reach, also raise questions about exposure, accumulation, and long-term interaction. Those questions do not negate the value of the technology. They reflect its integration into daily life. When a tool becomes ubiquitous, understanding its boundaries becomes part of responsible use. And so, from power generation to communication, from computation to medicine, electromagnetic fields form the connective tissue of modern technology. They are not accessories layered onto devices. They are the operational core. Recognizing this does not require technical expertise. It requires a shift in perspective. Machines are not boxes that do things. They are arrangements that shape fields. Networks are not abstract connections. They are coordinated patterns of electromagnetic activity. Once that shift takes place, the technological world becomes less mysterious and more continuous with the physical world. The same invisible forces that shape atoms and light also shape cities, networks, and systems. And as those forces become ever more tightly woven into human life, attention naturally turns to how they affect us directly, how safe those interactions are, how risk is assessed, and how misunderstandings arise when something essential remains invisible. As electromagnetic fields became inseparable from modern life, questions about health and safety followed naturally. Invisible influences tend to attract concern, not because they are inherently dangerous, but because they are difficult to sense directly. When something cannot be seen, heard, or felt, it is harder to trust intuition, and harder still to separate real risk from imagined threat. The discussion around electromagnetic fields has therefore often been shaped as much by uncertainty and misunderstanding as by evidence. To understand risk clearly, it helps to begin with a basic physical distinction. Not all electromagnetic fields interact with the body in the same way. The key factor is frequency, which determines how much energy is carried by each oscillation of the field. This single parameter divides electromagnetic radiation into two broad categories with very different biological implications. High-frequency electromagnetic radiation, such as X-rays and gamma rays, carries enough energy per oscillation to break chemical bonds. When this type of radiation passes through living tissue, it can damage DNA directly by ionizing atoms and molecules. This is why exposure to high levels of ionizing radiation is associated with increased cancer risk and other health effects. These risks are well established, well studied, and carefully managed in medical, industrial and scientific settings, lower frequency electromagnetic fields, including radio waves, microwaves, infrared radiation, and the fields associated with power lines and household electricity, do not carry enough energy per oscillation to break chemical bonds. These are known as non-ionizing fields. Their primary interaction with biological tissue is through the movement of charges and at sufficiently high intensities through heating. This distinction is not semantic. It is rooted in fundamental physics. An electromagnetic wave cannot cause chemical damage unless its frequency is high enough to supply the required energy in a single interaction. No amount of signal modulation, information content, or exposure duration changes this basic rule. Understanding this immediately clarifies many common misconceptions. A low-frequency field does not become more dangerous simply because it carries data or because it is used continuously. A radio signal transmitting music and a radio signal transmitting silence differ in information, not in physical interaction with tissue. The fields involved obey the same energy constraints. Heating is the primary known biological effect of non-ionizing electromagnetic fields at high intensities. This is not controversial. Microwave ovens work by delivering electromagnetic energy at power levels high enough to cause water molecules to rotate and generate heat. Industrial heating systems use similar principles. These effects are well understood and predictable. Safety standards are built around this understanding. Exposure limits are set far below levels at which significant heating occurs. These limits include large safety margins, accounting for uncertainties, variations among individuals, and long-term exposure scenarios. The goal is not merely to avoid immediate harm, but to ensure that everyday exposure remains comfortably within known safe ranges. Power lines, for example, generate low-frequency electric and magnetic fields. These fields decrease rapidly with distance. Measurements taken directly beneath transmission lines show field strengths that are still far below levels known to cause biological effects. Inside homes, fields from household wiring and appliances are typically much weaker still. Wireless communication devices generate higher frequency fields, but at much lower power levels than heating applications. Mobile phones, Wi-Fi routers, and Bluetooth devices operate within regulated limits designed to prevent significant tissue heating. The power emitted by these devices is small compared to everyday sources of electromagnetic energy, including sunlight. Sunlight itself provides useful perspective. Visible and infrared radiation from the sun delivers far more electromagnetic energy to the body than most artificial sources encountered in daily life. The warmth you feel outdoors is electromagnetic heating. The difference is that sunlight is familiar while artificial fields are often not. This familiarity bias plays a role in how risk is perceived. Natural sources tend to feel safer, even when they are objectively more intense. Artificial sources tend to feel suspicious, even when their physical impact is minimal. This emotional response is understandable, but it does not align well with measured risk. Large-scale scientific studies have examined potential health effects of long-term exposure to non-ionizing electromagnetic fields. These studies include laboratory experiments, epidemiological research, and animal studies. The results have been extensively reviewed by international health organizations. The broad conclusion that has emerged is consistent. At exposure levels below established safety limits, there is no reliable evidence of adverse health effects caused by electromagnetic fields. This does not mean that every study shows identical results, or that every question is fully settled. It means that no causal mechanism consistent with known physics and biology has been demonstrated at everyday exposure levels. One reason these questions are difficult to resolve conclusively is that biological systems are complex. Health outcomes are influenced by many factors, including genetics, environment, lifestyle, and chance. Detecting subtle effects against this background requires careful methodology and large data sets. Correlation alone is not enough. If a health outcome and an environmental factor occur together, it does not mean one causes the other. Establishing causation requires consistency, dose-response relationships, plausible mechanisms, and reproducibility. Many claims about electromagnetic fields fail to meet these criteria. This does not mean concerns should be dismissed casually. Scientific caution cuts both ways. It requires openness to new evidence and willingness to revise conclusions if reliable data emerge. But it also requires resisting conclusions drawn from anecdote, fear, or incomplete understanding. Another source of confusion comes from conflating different parts of the electromagnetic spectrum. High-frequency radiation hazards are real and well managed. Low-frequency fields are sometimes feared by association rather than by mechanism. Treating all electromagnetic exposure as equivalent obscures important distinctions. Public discussion is also complicated by the fact that electromagnetic fields are often discussed alongside chemicals, pollutants, or toxins. Fields are not substances that accumulate in the body. They do not leave residues. Exposure ends when the field is removed. This does not make them harmless by default, but it does make them fundamentally different from many environmental hazards. The concept of electromagnetic hypersensitivity is sometimes raised in this context. Individuals report symptoms they attribute to electromagnetic exposure, even at very low levels. These experiences are real to those who report them. However, controlled studies have generally found that symptoms do not correlate reliably with actual field exposure under blinded conditions. This suggests that while symptoms are genuine, they may not be caused directly by electromagnetic fields. Stress, expectation, and environmental factors can produce physical symptoms. Recognizing this does not invalidate personal experience, but it does inform how causes are understood and how solutions are approached. In medical contexts, electromagnetic fields are used deliberately and intensively, but under controlled conditions. Imaging systems, therapeutic devices, and monitoring equipment operate within well-characterized field regimes. Their benefits are measurable and significant. Their risks are understood and managed. This contrast highlights an important point. Electromagnetic fields are not inherently harmful or beneficial. They are physical phenomena. Their effects depend on strength, frequency, duration, and context. Risk assessment is therefore a matter of degree, not presence. Regulatory agencies around the world continuously review scientific evidence and update guidelines as needed. These guidelines are based on international consensus and incorporate conservative assumptions. They are not static, but they are not arbitrary either. Understanding how these guidelines are developed helps clarify why certain exposures are considered acceptable. They are not based on assumptions of zero effect, but on observed thresholds, safety margins, and biological plausibility. Fear often fills the gap left by invisibility. When something cannot be sensed directly, it becomes easier to imagine worst-case scenarios. Clear explanation and transparent measurement help counter this tendency. Education plays a role here. When people understand that electromagnetic fields follow specific rules, that those rules constrain possible effects, and that exposure levels can be measured accurately, concern often shifts from anxiety to informed awareness. This does not eliminate all questions. Science is not about eliminating uncertainty entirely. It is about narrowing it and understanding its boundaries. Ongoing research continues to examine long-term exposure, combined effects, and emerging technologies. What matters is proportionality. Risk should be assessed relative to evidence, not amplified by mystery. Electromagnetic fields deserve careful study because they are widespread and important, not because they are unknown or inherently dangerous. Seen in this light, the story of health and electromagnetic fields is not one of hidden threats lurking in everyday life. It is a story of how physical understanding guides safety, how invisible phenomena are brought under rational control, and how modern societies learn to live responsibly with the tools they create. As understanding deepens, focus gradually shifts away from fear and toward perspective. Electromagnetic fields are not anomalies in nature. They are part of the same fabric that makes light possible, that allows nerves to fire, that lets technology function. And once the question of risk is placed in that broader context, another more reflective question emerges. Beyond safety and utility, what do electromagnetic fields tell us about reality itself? Do they merely transmit forces, or do they reveal something deeper about how the universe is structured and how our descriptions of it have evolved over time? By the time electromagnetic fields are understood well enough to be measured, engineered, regulated, and woven into daily life, a quieter question begins to surface. It is not a question about devices, safety limits, or applications. It is a question about meaning, about interpretation, about whether fields are something we invented to describe reality, or something that was always there, waiting to be recognized. At first glance, the question may seem philosophical rather than scientific, but it arises directly from physical practice. Fields were not discovered in the same way planets or elements were discovered. No one stumbled across an electromagnetic field in nature and pointed to it as an object. Fields emerged as a way to make sense of consistent patterns, of forces that acted across space, of energy that appeared to reside where no matter could be found. This raises a fundamental issue. When we say a field exists, what do we mean? Are we naming a physical entity, something that occupies space and carries energy? Or are we naming a mathematical structure, a useful abstraction that helps organize observations without claiming independent existence? Early resistance to field theory was rooted in this ambiguity. For centuries, physics was built around tangible things: particles, objects, bodies in motion. Causes were expected to be mechanical. Contact mattered. Distance was bridged through collisions or intermediaries that could, at least in principle, be imagined as solid. Fields disrupted this picture. They shifted attention away from objects alone and toward relationships. Instead of asking what one object does to another, physics began asking what conditions exist at each point in space. This was a profound change, and it did not sit comfortably with older intuitions. One way to approach the question is to ask whether fields do real work. Electromagnetic fields carry energy. They can move objects, they can heat matter, they can exert pressure, they can store energy and release it later. These are not metaphors, these are measurable effects. If a capacitor stores energy, where is that energy stored? Not in the metal plates alone. It resides in the electric field between them. Remove the field, and the energy is gone. This is difficult to reconcile with the idea that fields are mere bookkeeping devices. Something real is present. Similarly, electromagnetic waves propagate through empty space, carrying energy and momentum. They can push objects, trigger chemical reactions, and deliver information across vast distances. There is no underlying substance being transported. What moves is the field configuration itself. From this perspective, fields look very much like physical entities. They occupy space. They evolve over time. They obey laws. They interact with matter and with each other. They can exist in regions where no particles are present. At the same time, fields are not objects in the everyday sense. You cannot isolate a field and place it on a table. You cannot observe it directly without seeing its effects on something else. Fields are always inferred, never directly perceived. This duality complicates the question. Fields are real in their effects, but elusive in their substance. They do not behave like matter, yet they are not nothing. One response is to say that fields reveal structure that was always there. According to this view, the universe is fundamentally field-based. Particles are secondary, emerging as localized excitations of underlying fields. Matter itself becomes a manifestation of field behavior rather than a separate category. This idea is not speculative. In modern physics, particles are often described precisely this way. An electron is not a tiny solid bead. It is an excitation of an electron field, Photons are excitations of the electromagnetic field. What we experience as matter and radiation are different patterns within a field framework. If this is the case, then fields do not merely describe reality, they constitute it. They are the medium through which interactions occur, the substrate from which particles arise, and the mechanism by which energy and information move. Another response takes a more cautious stance. It argues that fields are powerful models, not necessarily ontological commitments. According to this view, fields are tools that summarize how objects behave, without claiming that the field itself is a thing. What matters is predictive accuracy, not metaphysical interpretation. This instrumental approach has a long history in science. Many concepts have been introduced because they work, not because their underlying reality is settled. Atoms themselves were once treated this way. They were useful models long before they were directly observed. The difficulty with applying this stance to fields is that fields increasingly appear in places where there are no objects left to explain. In empty space between particles, fields remain active. They do not vanish when matter is removed. They have their own dynamics. This makes it harder to maintain that fields are only summaries of object behavior. They seem to have autonomy. There is also a historical dimension to the question. Fields were not obvious. They required a shift in thinking that many resisted. That resistance was not irrational. It reflected a deep commitment to a worldview where reality was composed of tangible things interacting through contact. Accepting fields required letting go of that picture and embracing something more distributed, more abstract and less intuitive. Space itself became active. Empty regions gained properties. Influence no longer required touch. This shift mirrors other moments in science where familiar categories were stretched or replaced. Time was once thought to be absolute. Space was once thought to be passive. Matter was once thought to be indivisible. Each of these assumptions gave way under pressure from evidence. In that sense, fields may not shape reality so much as reveal it. They expose aspects of the universe that were always present but not easily described within older frameworks. At the same time, it is undeniable that the language of fields shapes how reality is understood. Once fields are adopted, certain questions become easier to ask, and others fade into the background. Focus shifts from objects to configurations, from trajectories to distributions, from local causes to global patterns. This shaping influence matters. Scientific descriptions are not neutral mirrors. They guide attention. They influence intuition. They determine what counts as an explanation. The field concept encourages thinking in terms of continuity rather than discreteness. It emphasizes local interaction over distant action. It makes energy and information flow central rather than incidental. These emphases have consequences far beyond electromagnetism. They influence how gravity is understood. They influence how quantum systems are described. They influence how space and time are modeled. In this way, fields both reveal and shape reality. They reveal underlying regularities by capturing how influence propagates. They shape understanding by providing a framework that highlights some features and downplays others. This is not a flaw. It is an inevitable aspect of scientific progress. No description is final. Each framework opens possibilities and introduces limits. What makes electromagnetic fields particularly instructive is that they sit at the intersection of abstraction and experience. They are described mathematically, yet they power devices, light rooms, and drive communication. They are invisible, yet indispensable. They force a reconsideration of what it means for something to exist. Existence no longer requires solidity. It requires consistent causal influence. If something affects outcomes in predictable ways, carries energy and obeys laws, it earns a place in the inventory of reality, even if it cannot be held. From this perspective, the universe looks less like a collection of objects floating in emptiness, and more like a continuous fabric of interacting fields, with objects appearing as stable patterns within that fabric. This view does not eliminate mystery. it relocates it. Instead of asking how objects reach across space, we ask why space itself has the properties it does. Instead of asking why forces act, we ask why fields obey the rules they do. These questions do not have simple answers. They point toward deeper theories, deeper unifications, and perhaps deeper revisions of intuition. What electromagnetic fields make clear is that reality does not have to align with human-scale experience to be real. The structures that matter most can be invisible, continuous, and counterintuitive, and once that is accepted, it becomes easier to see modern physics not as a departure from common sense, but as an extension of it, a gradual widening of perspective driven by evidence. The field picture invites humility. It reminds us that the categories we use are provisional, that what feels solid may be emergent, that what feels empty may be structured. In this sense, electromagnetic fields are not just tools or curiosities, they are lessons. They show how understanding deepens when attention shifts from appearances to relationships, and as that shift settles in, it becomes natural to step back one last time, not to close the discussion, but to reflect on how living in a world shaped by invisible forces changes how we relate to the familiar, the ordinary, and the seemingly simple aspects of existence that are quietly sustained by fields we never see. By the time we reach this point, electromagnetic fields no longer feel like a special topic set apart from the rest of reality. They feel woven in, present in the background of everything discussed, quietly supporting motion, structure, and connection without ever asking to be noticed. That perhaps is the most accurate way to think about them, not as hidden forces waiting to be revealed, but as familiar companions we've always lived with, even before we had words for them. Living with forces we never see does not require constant awareness. You do not need to imagine fields flowing through a room in order for a light to turn on or a signal to arrive. The success of electromagnetic technology and of the scientific framework behind it lies partly in how completely it disappears into function. When something works reliably, attention moves elsewhere. Yet invisibility does not mean absence. The fields are still there, shaping outcomes whether or not we think about them. Every electrical device around you is embedded in an environment structured by electric and magnetic conditions. Every wireless signal moves through space already filled with other signals. Every biological process inside your body unfolds within a web of electromagnetic interaction. What changes, once this is understood, is not how the world works, but how it is interpreted. Ordinary experiences take on an added layer of coherence. A lamp is no longer just an object that produces light. It becomes a point where charges accelerate, fields oscillate, and electromagnetic waves spread outward. A phone call is no longer a mysterious connection across distance. It is a carefully shaped disturbance moving through space, decoded at the other end. Even silence has a different meaning. A quiet room is not electromagnetically empty. It is simply not interacting with your senses in obvious ways. Fields still pass through. The planet's magnetic environment still holds. Radiation from distant stars still arrives, mostly unnoticed. The absence of perception does not imply the absence of structure. This realization can be grounding rather than unsettling. Invisible forces are not unpredictable forces. They follow rules that have been tested, refined, and relied upon for generations. The same principles that explain a compass needle turning also explain global communication networks. The same equations that describe light also describe radio waves passing through walls. Understanding this continuity removes the need for mystery where none is required. Electromagnetic fields are not secret influences acting beyond comprehension. They are among the best understood aspects of the physical world. Their behavior is constrained, measurable, and consistent across scales. At the same time, understanding does not drain the world of depth. If anything, it adds to it. Knowing that space itself carries structure, that energy can move without matter, that influence does not require contact, expands the sense of what reality can be. The visible world becomes a surface expression of deeper processes operating quietly beneath it. Living with forces we never see also invites a certain kind of attentiveness. Not vigilance, not anxiety, but awareness. Awareness that systems are interconnected, that actions ripple outward through shared environments, that technology is not separate from nature, but an extension of it, using the same invisible rules that govern planets and cells. This awareness has practical value. It encourages responsible design, thoughtful regulation, and informed use of technology. It reminds us that managing electromagnetic environments is not about eliminating fields, but about shaping them wisely. It also has a reflective value. It shifts perspective away from objects as isolated things and toward relationships as fundamental. What matters is not just what something is, but how it interacts, how it influences and responds. Fields make those interactions visible in principle, even if they remain invisible to the eye. In this sense, electromagnetic fields are less about control and more about connection. They connect charges to charges, devices to networks, organisms to environments, planets to stars. They allow information to move, energy to flow, and systems to coordinate without physical contact. Once this framework is in place, the world feels less fragmented. The same invisible structures appear again and again in different contexts, wearing different faces: electricity in a wire, light in the sky, signals in space, activity in the brain. None of these are separate stories. They are variations on the same theme, and that theme does not end here. The field-based view continues to shape how gravity is understood, how matter is described at the smallest scales, how space and time themselves are modelled. Electromagnetic fields were not the final discovery. They were a turning point. What they teach, more than anything, is that reality does not need to announce itself to be real. Some of its most important features operate quietly, consistently, and out of sight. Learning to live with that fact is not about seeing more. It is about understanding more. As you move away from this moment, back into whatever surrounds you physically, nothing has changed in the environment itself. The same fields remain. The same interactions continue. What may have shifted is only the sense of context. Lights will still turn on. Signals will still arrive. The planet will still hold its magnetic shape. Cells will still communicate electrically. All of it will proceed as it always has. But beneath the ordinary flow of experience, the invisible structure remains, steady and active, shaping the world not as a hidden threat or distant abstraction, but as a constant presence that has always been there, quietly doing its work, whether or not anyone is paying attention.